Hello Matrix, and welcome to this video, and I hope you guys have been doing very well in the exams that you've already written. I hope you were able to benefit from some of the exercises we had to put up. Apologies for not being able to meet some of the requests that you guys have made. I'm aware Mandlov wanted me to do paper 2 from Gauteng, but due to time effect, it just could not happen. I kind of fell sick on Friday, so the whole weekend I was inactive, so I could not post anything on that. Apologies, but I hope all the other videos that have been made were able to give some sort of an aid. And then of course every other channel on the platform, there is a lot of information there. Now that mathematics is on the side, let's focus on the physical science, which we're going to be dealing with the Limpopo paper written in September Trials 2022. So it's quite an interesting paper, so I figured let me just use this one as the revision for our physical sciences. So let's just get to it without wasting too much time, and I hope you will learn something through it. Now, question 1, we know the instructions. We cannot overly emphasize the importance of reading the general instructions so that when you come to local instructions, you can know when they fit and when they don't fit. Okay. Now, 1.1 says a body. Let's just get a nice color here. Okay, it's already there. A body is moving at a constant velocity. So these are some of the words that you're already familiar with. So constant velocity. Now remember, that is already a keyword. What does it tell us about the motion of this object? It means it has a zero acceleration and a net force of 0. So it says now the net force acting on it is definitely 0. So questions like these, if you interpret a little bit of the statement that you're given, you already have an answer. You're not going to be wasting your time with other things like figuring out what those are. You already know that once there's a constant velocity, it means the net force is 0 because the acceleration is 0. So the rest is not important. Okay, let's keep moving. And then an astronaut has mass m and a weight w on Earth. So what is the mass of the astronaut on Earth? It's m. And what about his weight or her weight on Earth? It is w. Okay, so now we are told that the planet X has twice the mass and twice the radius of the Earth. Okay, so everything is doubled. Now it says, which one of the following combinations best describes the mass and weight of the astronaut on planet X? Okay, now here you've got two options. You can do the calculation or you can just figure it out. Let's just see. First of all, the mass is constant. It's a scalar quantity. It never changes depending on where you are. So we know that every option that has mass m for the astronaut is important. And then everything else that says otherwise, I mean, the mass cannot be twice or half because the mass is just the mass, all right? But the weight, yes, will definitely change. So we know that, well, the weight cannot be B. I mean, it cannot be W on a planet where, the radius of that planet is twice that of the Earth and the mass of that planet is twice that of the Earth. So because of that, that one falls away. Okay, so we know that. Well, thank you very much. You have been able to give us an answer, and now we simply choose our A. Of course, you can go on and do a calculation. It is fine. It's not a big deal. But questions like this, don't let them waste your time, because if you can be able to eliminate all the other options, the remaining should be the answer. And then, of course, when you come back, when you have time, you can have a look and see if indeed you're not making an error there. Okay, so 1.3 says two identical balls. Okay, now that is this keyword over there, identical. X and Y, okay, are thrown from a certain height. Okay, so they are already a height above the ground. So this is this height over here. Okay, so we can see there that, well, we have our ball X and we have our ball Y. Okay, not a problem. So each with the same speed. Okay, now that is the most important also, that the speed is the same. All right, so meaning this one is thrown straight down with the same speed as this one thrown upward. Okay, so ball X is thrown vertically downwards and ball Y vertically upwards as shown in the diagram. Okay, not a problem. Now if we can just draw the trajectory of what will happen to this ball will reach some maximum height and then come back down to the ground, whereas this one just goes straight down to the ground. Now let's have a look here. Remember, the velocity or the speed with which this ball leaves, it will be the same speed it will arrive at the same height on its way down. So it's only negative, because if you choose up as positive, for example, and then that means down would be negative, or you choose down as positive and then up would be negative. But the good thing is, the idea is this velocity here is the same as that there, meaning even though this ball is going to take much longer to go around the way all the way to the ground, but as soon as it reaches that height from which it was released, it will be moving at the same speed. That means this ball also is going to leave that same height with the same speed as that one. And of course, we know the acceleration is that of gravity. So they'll be accelerating due to gravity all the way to the ground. So it means the velocity for ball X, let's say the final velocity for X, is going to be the same as the final velocity for Y. Why? Because they leave the height at the same speed and they're accelerating due to gravity. So the fact that it went all the way up doesn't really matter, because at the end of the day, when it comes back to that same position, its displacement is zero. So it is effectively being displaced from this position of its initial launch to that one, which is just that distance, is the same as that, not distance but perhaps position or displacement. Okay, so that is the story here. So it says now, how does the speeds and the kinetic energies of the balls compare when they strike the ground? Remember, when we say the balls are identical, mainly we are talking about the mass, right? And then maybe the spherical space as well, meaning the volume they occupy in space would be the same. All right, so they have the same mass, they leave the same height with the same velocity somewhat, and essentially they will be accelerating due to the same magnitude of acceleration, which is that of gravity, and therefore they will hit the ground with the same final velocity. So that means if the velocity is the same, so we can just say Vfx is equal to Vfy, because of the same concept we just explained. And then what is going to happen here? Now, what about the speeds? They should be the same, right? Yes. And then what about their kinetic energy? If they arrive on the ground with the same speed and they have the same mass, they'll definitely have the same kinetic energy. So anything that says otherwise is already out. So this is out. Anything that says there's an inequality there is out. So our answer is C. Okay, so I hope that is very easy to tell. Okay, but other questions are not as easy as that, so don't be too eager. Now 1.4 says two masses of 1 kg and 4 kg are moving with equal kinetic energies. Okay, So now that is very important. Now it says the ratio of the magnitudes. Now what do we want? We want the ratio of the magnitudes of their momenta. What is it? Now this is not something that you can just look at and just pick an answer. Now unfortunately you are forced to do some sort of a calculation. But what do we know? We know that if we say the kinetic energy is EK, it is going to be equal to half, and then of course for that 1 kg mass is going to be 1 multiplied by V. We can just call it V1 squared because that is for the 1 kg. And then of course this basically tells you and I that we have a half V squared, giving us our EK. Okay, so this is the first instance. Now what about the second instance? If we look at this one, also because this we are told is the same, so we're going to just call it EK is equal to this is going to be half, the mass is 4, and then we can call it V2 squared. That is great. And then we solve this further, it becomes 2V squared, 2V2 squared. Okay, make sure there are subscripts that separate these things so that you don't make a mess of things here. Now what do we know? We know that these two, this guy over here is the same as this guy over here. All right, why? The statement says so. So this implies what? We know that half V1, this is V1, sorry, half V1 squared is equal to 2V2 squared. All right, great. And then of course this is over 1. If this is a fraction, you just cross multiply that. What do we end up with? We know that V1 squared is going to be 4V2 squared, isn't it? Yeah, because if you cross multiply, remember 1 times 1 is just 1. And then of course, what do we want? We want to deal with momentum, so you take the square roots on both sides. This is going to say V1 is equal to 2V2. So this is most important because we want this information. Once we know the relationship of their velocities, then we can be able to make an argument about their momenta. So now let's look. V1 is 2 times V2, meaning V2 is a half. Wait a minute. What am I saying now? Yeah, V1 is 2 times the velocity of the second object. Okay, that is M. Let's just call this one M1. Sorry, M2. Whoop. Let's call this one M1. No. M2. And then this guy. And I'm not interested in doing that today. M1. Okay, so what do we know of it is that twice the velocity of the second object is equal to the velocity of the first object. So meaning we can use this one to relate these two velocities. Okay, V2 is just V2, but we know that 2 times V2 is essentially giving us V1. So what does that tell us? We can say now the P of the 1 kilogram, meaning the momentum of the 1 kilogram object, is going to be its mass, which is 1, multiplied by its velocity. Remember, V1 was the velocity for that object, so it's going to be 2v2, right? Because from this equation we can tell that that velocity is going to be double. Okay, so which is the same as 2v2. So the momentum of the 1 kilogram block is 2 times v2 basically, which is the same thing as that. What about the momentum of the second object? It is going to be 4, which is its mass, multiplied by v2, which is its velocity. Okay, so all we wanted was just to be able to relate those two so that we can be able to deal with this ratio nicely. So basically this is basically 4v2, so 2v2 and 4v2. Now we can go on and say now the p of the first object over p of the second object is going to be equal to, what is that, 2v2 over 4v2. Okay, Now that cancels, that once, that twice, which is just 1 over 2. So 1 over 2 represented as a ratio is 1 is to 2. So what is that? That is this answer here. So here you can't guess, unfortunately. I mean, even if you decided to take, say, this one over that, you would still get 2 and 1. And even if you reverse the ratio, it doesn't really matter as long as it represents the same thing. So it won't change. It will still be A. Okay. So that's all right, guys. So I'm just going to take out this one because I've just used this space to work our magic. So you can already tell this is a question that would award you some 4 marks, some 6 marks if it was asked in the long questions. So you unfortunately have your time stalled there. 1.5 says when the net work done. What is that? The net work done on a moving object. So the object is moving, it's not stationary, is 0. So when now work done on an object that is moving is 0, it says its kinetic energy is what? Is constant. I mean, you have to think about it. We know that our net work done is equal to the change in EK of an object. Now change is basically the EK final minus EK initial, right? So if this is 0, it means these two are equal. And when these two are equal, that means that is constant. All right, so easy. 1.6 says spectral lines from the distance, okay, not distance, but distant, okay, from a distant star, which is from a galaxy, moving away. So we're moving away from the Earth. Now, when we move away, we're talking about a red shift. Okay, so that's a red shift. So red shift means longer wavelengths. Yeah, ne? And then, of course, if that's a longer wavelength, it means shorter frequencies. Okay, so that is the story that we're talking about when we're talking about this. I mean, excuse my writing ability there. It's just, not getting any better. Okay, so now when we have a red shift, we are shifting towards longer wavelengths and shorter frequencies. Okay, so now it says 1, this is lower frequencies, which is true. Higher frequencies, no. Higher frequencies means shorter wavelengths, ne? And that is a blue shift. So shorter wavelengths, no, it can't be shorter wavelengths, right? It's longer wavelengths. And then is it the longer wavelengths? Yes, that is true. Now question is, which of the statements above are correct? So is it 1 and 2? Anything that has 1 can be considered, but because of this guy, this is already wrong. Well, 2 and 3, they are together wrong. Now anything that has 4 is correct, but 2 is making it entirely wrong. So our answer becomes D, because we are confident that those 2 are the most important. Again, this is an exam type question that you can find in the finals, so be able to do a bit of a small revision and make a decision. Otherwise, these questions can be easily attempted, although they can pose a bit of a challenge. Okay, no problem. Next question says 2-point charges X and Y produce a net electric field. So the most important thing, it is the net electric field at P, which is directed to the right as shown. Okay, so that is what we're talking about. So there's our net electric field. Okay. Now the question says, which one of the following combinations of charges X and Y cannot have? Okay, sorry, meaning which one of the following combination of charges, meaning X and Y, cannot have, meaning that is not possible to give us this net effect. All right, so we have to look at this. All right, now it says A, X is positive and Y is positive. Is that possible? The answer is yes, because we know that a positive charge basically has the electric field directed away from it, and then if you place another positive charge, the electric field goes away. Now that means at this point we have an electric field that goes that way. So yeah, that is possible. So that is true, meaning it is not the answer, because we want the one that is not possible to give us this. Now B, can X be negative and Y be positive? Definitely, because we know that the negative charge will actually be pulling towards it. The electric field is going towards the center of that charge. But if there's another positive charge here, that one is doing that. They oppose. But remember, the distance between point P and that negative charge is quite large, and you know, once that distance is bigger, once you increase the denominator from knowing that electric field is given by kq, whichever q we're talking about, over r squared. So increase on the denominator, you are decreasing the net electric field. So that means the electric field due to that negative charge over that larger a distance compared to an electric field of a positive charge over a short distance, definitely this one will overpower and force the electric field to be in that direction. So that is possible. And then C, can this be positive and that one be negative? Well, that is possible. Why? Because we also know that the electric field, if we think about it that way, remember what is on the numerator is the charge. Now let's imagine we have a positive charge here and then a negative charge. Of course, the negative charge would be trying to pull the electric field towards its center, while that one is pushing it away like that. Now these two are opposing each other. But remember, if this charge is large enough, okay, it means even over a longer distance, it may still have a very strong electric field if this magnitude of charge is greater, okay, because the electric field is directly proportional to the magnitude of the charge itself. So we can have a positive charge here, but a much bigger magnitude than would be the magnitude of this charge, despite the fact that it will be acting at a shorter distance, at point P. So that is possible, okay, but on the constraint that the magnitude of this charge should be way bigger than the magnitude of this charge. All right, so that is acceptable. But can this be negative charges? The answer is definitely not. And if it is not, it is our answer, because we want this not to be the case. Why is it not possible? Remember, this would be like directing this one that way, and then this charge over here, if it is negative also, remember this is point P, this one is also pulling it that way. So these are in the same direction, so the net would be directed to the left. So that's why it is not possible for it to be in there. Okay, so let's keep going, guys. We're almost done. Now, two identical resistors. So when we're talking about identical resistors, it means they have the same resistance, or the magnitude of the resistance, are connected in parallel as shown in the circuit diagram below. The internal resistance of the cell and resistance of the connecting wires can be ignored, okay? So once we talk about internal resistance and that of the wires to be ignored, it means the EMF of the cell is essentially the voltage of the external circuit. All right, not a problem. So that means the EMF is exactly the energy that is supplied directly into the external circuit. Now, we are told here, when switch S is open, which is over here, the reading of the ammeter is I. So meaning this one reads I over there. And this I will only pass through which resistance? Only this resistance here. There will be no current passing through here, because once this switch is opened like this, this creates a very high resistant segment here. It is negligible, not negligible, but infinite, right? So whenever you hear a word that says infinite resistance, it tells you that that resistance is too large, that no charge would pass through there. This is stuff like a galvanometer. No, I'm lying. A voltmeter, okay? It's a voltmeter, not a galvanometer. All right, so this, once the switch is open, you're creating a high resistance segment here, meaning charge will not be able to pass through here. So it will just pass through the lesser resistant part. And then of course charge only goes when the circuit is complete. Okay, just think of that as well. So what happens now when this switch is closed? So when the switch S is closed, the reading on the ammeter, which is still this one, and maybe let's not do that. Let's give it another color. Okay, guys, make sure when you do MCQs, you don't go longer than 30 minutes, which I'm going to try not to surpass. Now, what do we do here, guys? When we close here, remember, when these are in parallel and they are identical, now that means we're going to halve the resistance. So the effective resistance here, or should we say R parallel, is going to be half R. You can do that by saying you're going to be having a product over sum, right? The sum is going to be 2R, right? And then the product is going to be R squared, but 2R in the denominator, let's just say R parallel is going to be the product, which is R squared, over sum, which is going to be 2R, because it's going to say R plus R. This R takes that one. So do you see we end up with that? So we are halving the total resistance. And what happens when we have the total resistance? Remember now our voltage is the EMF, so it remains constant. So basically we're going to end up with doubling the total current. So the current should be doubled actually. If we're halving the resistance, the current is going to be doubled. Okay, so meaning the total current that passes here is going to be 2I. All right, and then when it gets here, it splits because these resistors are identical, so it's 1:1. So this will split into I and then I on this side. Okay, so that means this ammeter will read I. So the answer there becomes A. So everything else goes away. All right, I hope you understand that. It is built from Ohm's law. All right, guys, let's keep moving. We don't want to waste time here. The following information is given on a household electric appliance. Okay, and it says now 230 volts and 500 watts. Now the value 230 volts refers to, is it the peak value, meaning the peak voltage? The answer is no. So always whenever you are given some sort of a home appliance, remember we're talking about an AC current because our households are supplied with an AC current, not a direct current. All right, direct current machines is your hair dryers and other things that you use in the house, but everything else gets an AC source. That means your household from your power lines. Now if we have an appliance that uses this 230, we know that that is our RMS. It's a root mean square voltage. Okay, so what is that? Is it half of the value of the peak voltage? Not really. It's an RMS value of the voltage. The answer is yes. So it's not that and it is not that. All right, guys, so let's do the last one quickly. On which one of the following does the number of photoelectrons ejected? Now remember, once we talk of a number of photoelectrons ejected per unit time, it depends on the intensity of the light, isn't it? Intensity, it means more photons. We know that one photon is to one electron, right? So if you want a number of these, that means you must have a number of photons is going to be equal to a number of electrons, right? So that means our N here goes with the N, okay? Because each photon will empty all its energy into exactly one electron. So intensity always tells us about a number of photons, not just one photon, but a number of them. So it depends heavily on that. So that becomes our answer. So some questions are very easy. You can answer them at a go, but others you have to think about them a little bit more. The frequency of the incident light, now it only tells us whether we can eject or not, but it doesn't tell us about how many electrons are going to come out. It just gives us the idea that will there be electrons emitted or not. If it is a threshold, again, if it is above the threshold of the metal that we're shining the light on. The wavelength of the incident light, again, is more or less the same thing as that of the frequency, but they kind of go vice versa. Higher frequencies, and here that means shorter wavelengths. All right. Threshold frequency of the metal not necessarily tells us about the number of electrons, but it tells us whether we will be able to emit electrons or not. So the answer is A. Okay, exactly 30 minutes, guys. We've answered question 1. So I hope you have been able to follow easily there without any issues. So now let's do question 2 now. This is where the action is coming. All right, so let's do what we do best. Okay, we're going to answer stuff now. All right, we're told a crate is placed. Now remember, this is a crate is placed on a wooden plank. So there's 2 objects here. So you can see that there is a crate, there is the wooden plank, okay, which is pulled along a surface inclined at an angle of 10 degrees. Okay, so we have our angle there, not a problem, it's 10 degrees. By force acting parallel to the incline as shown in the diagram. So remember, on which object is this force applied? The force is applied on the plank, okay, but this is resting on the plank, okay, so meaning it can go with the plank as a unit. All right, great stuff. Okay, is there anything more? Not necessarily, but now let's analyze this diagram. What are the possibilities? From when we were small. Okay, why do I say we? Because you guys are smaller than me, and come on, cannot be a we kind of a situation. When you guys have been little, you were able to put a box on a paper. When you pull slowly, that paper would move with the box nicely, right? But if you pull the paper fast, the box may actually be dropped or may even be left behind. All right, so meaning for this to go together with this, there has to be friction between the box and the plank. And what is that friction? Now obviously, if it is one that keeps this one resting on this, it's gonna be static friction. But now in which direction? If we are moving in that direction, that frictional force should be in that same direction. Okay, maybe let's use another color here. So meaning there has to be some sort of a friction between these two. And in which direction is it directed? It's directed upward. Because for this crate to go together with this one, that friction must be opposing the weight, because the weight of this box will be trying through its parallel component to move this box that way. That would be FG parallel of the crate, okay, not of the plank, because the weight would actually try to not have this crate moving that way. So that means the friction here has to be greater than our FG parallel for this box, for this crate to move together with the box in that direction. Okay, these are some of the things you want to think about quickly as you look at the diagram. Now, the diagram is not drawn to scale, which is fine. Now, we're told here the maximum coefficient of static friction is 0.35. Okay, that is important. That means we're going to have to determine the value of that frictional force. Now, the question comes, define the term static friction. All right, guys, so definitions is stuff that you guys need to know, and to know well. There's no excuse for not knowing definitions. So how do you sort out definitions? Now remember, static friction is the force that we have to overcome to move a stationary object. If a stationary object is just stationary, for us to move it, we have to overcome the static friction. So how would you define it? You can say it is the frictional force okay, that a stationary object must overcome, okay, in order to be set in motion. Okay, it is a frictional force that a stationary object must overcome in order to be set in motion, or that we have to overcome in order to set that object in motion. Okay, that's an easy 2 marks. Okay, so let's just start here. What is that? That is 2.1.1. I'm not going to be starting with other things, so we have 2.1.1. okay, no, that is not the color for writing. Okay, let's do it nice and easy, guys. 2.1.1. So we are defining static friction. Okay, so how do we define it? It is a frictional force okay, that has to be overcome, or I don't know, that has to be opposed. You can even use that word opposed. Maybe that has to be overcome, okay, in order to set in motion. This chair is moving now. In motion a stationary object. Okay, so I mean, my writing is not the best, but you just see it. Static friction is a frictional force that has to be overcome in order to set in motion a stationary object. The most important thing is that this is a force, okay, and this force has to be overcome in order to move what? A stationary object. But we need to set that object in motion. So I mean, make sure whatever where you put your definition, it doesn't take away the essence of what the physical quantity or the physical phenomenon is. Okay, you get your 2 marks there. Then we are told here, draw a labeled free body diagram of the crate as the plank accelerates up the incline. So we're dealing with the crate. So how many forces are acting on the crate? As we established, there's 2 forces primarily that are acting in the direction of motion of this object. It is the force of gravity. Of course, it will be the parallel component, and then the frictional force. And then, of course, there's one other force that always acts, is the normal force. Okay, the normal force will be going that way. So you can do that, but I mean, I think the safest is just to show the force of gravity directed down like that. Show the frictional force and the normal force. We forget about these components. But if you want to do components, then you'll forget about that one of gravity, and then we may have to focus on this one and say this is going to be FG perpendicular. So it's up to our choice. But if you do these components, you get 1 mark for both. Then you get a mark for this one, you get a mark for the normal force. So let's do the body diagram. Not too big a deal. So if we think about it, we will have our force of friction, that is static friction, and then we always have this one acting perpendicular to the surface. Remember, the frictional force is parallel to the surface, so we will have our normal force, and we have our weight acting straight down. So I'm just gonna do that because I mean, it's just 3 marks, but you can resolve it to components. But always make sure you show there that there is some 90-degree angle. I don't know if it is necessary, but I think so. So this is friction, this is static friction, and that is going to be the weight or Fg. Okay, force of gravity. Then of course these symbols are acceptable, by the way, so you don't necessarily have to write them down in full, that this is normal force, this is Fg, this is Fs. So if you're looking at the guidelines, they actually accept these symbols. Fg is taken for force of gravity, or you can use capital letter W. Okay, and then capital letter N is always taken as the normal force, and then the small letter F is frictional force. All right, then this subscript S meaning static friction. If you write K, it means kinetic friction. Okay, so no need to stress about writing a lot of things here. Okay, not a problem. So we get our 3 marks there for these guys over there. All right, let's answer the next question. It says now, big one, eh? That's a big one. That's a big one. That's a big one. This one wants a calculation. Calculate the magnitude of the maximum acceleration that the plank can attain before the crate begins to slip backward. Meaning, we want the acceleration that this plank can have such that this crate doesn't fall off the plank. I've done a question like this, guys, using the IEB question paper from 2020. So you may want to go and have a look at that paper. On the, I don't know what question it was, but it was, yeah, there's a question I've done there for Newton's laws of motion or whatever. Please go and have a look at that. It has the similar idea. So those of you who were in Limpopo and saw that video, you must have smiled when you saw this, because it's the same concept, because there's force right there. Was done that way. So now what are we supposed to do, guys? Well, we know for a fact that, look, for this crate to be able to hold on to this plank, it means this static frictional force must not be overcome by this force, because if this force overcomes this one, then this one will start falling off, right? So basically it tells you and I that we are to have a situation where our Fs is literally our Fa. So that is what this means. Our applied force should be exactly the same as our frictional force there. Then it would mean that would be bigger than our Fg parallel of the crate. Okay, do we know the mass of the crate? We don't. So yeah, we have a bit of a challenge here, because now there's quite a few unknowns, but we will find a way. So of course here, once we hear the word acceleration, we think of Newton's law of motion, which is second law. Okay, let's deal with this one that way. So we have 2.1 point, yeah, maybe this should be 3, and that should be 2. Okay, now guys, we know and understand that, look, that acceleration, basically, it means it should be exactly the same acceleration that this plank is having. I mean, this crate is having. So we can either decide to work on this frictional force against this Fg parallel, because I mean, if these two are equal and we're focusing on the crate, we can just use the crate to our advantage and say this is effectively that. All right, and that should be against this Fg parallel. So we are in a good position here. So we can just deal with this one that way. So we know that if we resolve our crate here into this structure, we will have here our, oops, not that one. We have our Fs against the Fg parallel of the crate, okay? And now we want the acceleration of this as a unit with that one. So meaning we can actually use these forces as, you know, our advantage, because we will have the mass of this crate included here. So we know that, well, second law says the resultant force is equal to ma. But for us to be accelerating at some acceleration, it means this guy must be bigger than that. So it means we must have our Fs minus our Fg parallel equals ma. Okay, And then what is Fs? Remember, the normal force in this instance is actually exactly perfectly balanced by our Fg. Is exactly perfectly balanced by our Fg perpendicular. So we can use our technique of knowing how to find Fg perpendicular to use it as our normal force. So do you see? You need to be a bit crafty here. You need to be a bit crafty. So let's see. For us to do this one, we know that this is going to be Fg perpendicular. Essentially, this is going to be Fg. So this implies that Fg perpendicular multiplied by the coefficient of static friction, right? Yes, that is it, minus the Fg parallel is going to be equal to ma. I'm just working it out. I mean, if you are quick, you can just write all of this at once. Okay, then we move on. What is Fg perpendicular anyway? Fg perpendicular is mass, which we don't know. So this is mass times 9,8, which is the gravitational acceleration. Remember, once we do Fg perpendicular, that one becomes cos of theta. Now, what is theta? Remember, theta is that angle of inclination of our slope, which is 10 degrees. So I'm just going to move on quickly this time. Okay, so we're going to say multiplied by that 0,35, which is the coefficient of kinetic friction, because remember, all of this represents the normal force in a way. So minus Fg parallel is again the mass, which we don't know, multiplied by 9,8 multiplied by, now remember, Fg parallel is going to be sine of 10 degrees equals the mass we don't know, the acceleration we don't know. All right, but now from here you can already tell that we can actually divide by m throughout, because what you do on the left hand side you must also do on the right hand side. So the m disappears, so we never have to worry about we don't have to worry about that. So now when we isolate a becomes this 9,8 times cos of 10 degrees times 0,35 minus 9,8 times sine of 10 degrees. Then let's do it on the calculator, nice and easy. So we have 9,8 times cos of 10 degrees times 0,35. Did I copy that one correctly? Times, you must guard against making mistakes. Okay, so that one is giving me a particular number, then we're subtracting here 9,8 into a sine of 10 degrees. Okay, so what I'm getting, guys, here our acceleration becomes 1,68 meters per second squared. Just use an arrow. You can just say upslope, but they said magnitude, but I always treat a vector as a vector, so you can just say upslope. So this is how you can deal with this question. Okay, makes life a bit easier, but you need to be very strategic and very crafty, otherwise this can hurt if you don't approach it in a way that makes life a bit easier. So again, studying the diagram and understanding what is going on will help a lot. And then of course, previous experience from previous practice will make the difference. So yeah, that is it. All right, guys, let's not even bother ourselves with where the marks are and things like that, but it is a 5-mark question. In physics, you always get a mark for, you know, a formula. So I think this formula is important. I mean, it boils down to something like that. You can get the mark there, you can get the mark here, but normally in physics you get a mark for actually copying the formula correctly from your thingy, but you need to know it by heart as well. I mean, there's no point in suffering here. And then of course, look, there were three substitutions that we probably had to do, which I think are significant. That substitution as a whole and this substitution as a whole is very important, okay? And what else? The gymnastic. I mean, it's maths, I know, and this is physics. But to divide by that m, to eliminate that m was critical to doing this calculation. So this division here, or the gymnastic if you want, is quite important. And then of course the final answer, because the rest is just the same, right? Right. So this is how you get those 5 marks. 1, 2, 3, 4, 5. Okay. Not a big deal, guys. Okay. So we are done with this question. So we are done. Pretty nice. Easy 5 marks there. So let's look at the second component of this question. We are told here the radius of the earth is 5 times is 5 times, and the mass is 153 times that of planet X, meaning planet X is 5 times smaller in radius and 153 times smaller in mass compared to the mass, to that of the earth. And I think I've done this question with my student here, and I may have fed him poison because I think I multiplied this to the mass of the earth, and this is not the case. Okay, so when we are told here the radius of the earth is 5 times, it means r, if we say radius of the earth is going to be 5 times the radius of the planet that we are talking about. Okay, so meaning what can we say, man? What can we say? Maybe let's do it this way and say the story here says the radius, if we say capital letter R is the radius of the earth, it is going to be 5 times the radius of planet X. Okay, so what does that mean? If you want to solve for the radius of this planet, so you can say the radius of planet X is basically what is the radius of the earth divided by 5, isn't it? That is the most important part. And then when you're told here the mass is 5 times that of planet X, again, we know that the mass of the earth, if it is capital letter M, is going to be 5 times, sorry, no. Getting too excited now. It's 153 times the mass of planet X. Now, if we want to solve the mass of planet X, it's going to be effectively the mass of the earth divided by 153, okay? So always try to make sure you understand your statements that are given to you, because if that is in order, everything becomes pretty easy. Now, see easy mark questions. State Newton's law of universal gravitation in words. Okay, so we have here our 2.2.1. So we want Newton's law of universal gravitation. Okay, so how do we define it? Well, it says every particle in the universe, okay, exerts a gravitational force of attraction to every other particle, okay? So what do we know? Every particle in the universe exerts a gravitational force of attraction to every other particle such that the force is directly directly proportional proportional to the product of their masses and inversely nako kwenzeka sekuqalile inversely proportional to the squared distance between them. Of course, I'm just trying to simulate you writing an exam here. As much as my writing is terrible, but you know this definition anyway. You don't really have to read it off here. So all we know is that every particle in the universe exerts a gravitational force of attraction. Okay, this force is of attraction. So keywords bafethu mazingalahleki ne, ningalenzi lo phutha, ningayenzi lo mistake. Asifuni abantu babhatyaze la, aribatle the mistake in that. Okay, leska force ho hang to every other particle such that the force is directly proportional to the product of their masses and inversely proportional to the squared distance between them. Of course, my writing needs a lot of work. Sorry, but you already know it, that it is terrible. So yeah, I've already apologized for it a long time ago. So leave me alone, please. Assemblief doch, or else I will donor somebody. Calculate the acceleration due to gravity on the surface of the planet X. Okay, now this is very key, guys. Okay, let's do 2.2.2. So we have man. What is it doing to me? 2.2.2. So we want the gravitational acceleration. Remember, the weight, isn't it? It's mg is equal to, well, we know that when we use the Newton's law of universal gravitation, we're going to have the gravitational constant multiplied by the mass of this planet multiplied by the mass of the astronaut. Of course, maybe I should do this here. That is the mass of the astronaut, okay, over r squared, meaning the distance between this astronaut and the center of that planet. Okay, nice. But now if we divide by ma here, meaning mass of the astronaut here, that one and that one cancels, right? So what do we end up with? We will have a gravitational acceleration in that planet being equal to g, which is our constant, multiplied by the mass of the planet divided by the radius squared of that planet, isn't it? Nice. So I was just trying to show you how you derive, how to solve this equation. Again, you do have this equation on your information sheet, so you don't have to really rely on this, but at times things make a bit more sense when you trace them where they come from a little bit, so that you are sure you're doing the right thing. So now let's continue. So what is our gravitational constant? Let me just get my information sheet here. That one I definitely need it. So it is 6. This chair is moving. So this is 6,67 times 10 to the minus 11, right? Into, of course, this is like that, and then maybe more. Then what is the mass of this planet? Remember, we said when we used the information of what they told us, we could already tell that the mass of this planet X is going to be mass of the Earth divided by 153. So the mass of the Earth here is what? Let me look for it. Mass of Earth is 5,98 times 10 to the exponent at 24. So that's a big number, but we said we're going to divide it by 153. Ne? Yeah, maniac. You understand now? Okay, guys. I didn't want to get 2 hours without finishing question 2, but yeah, whatever fit. I'll try to not waste your time here. And then of course, yeah man, why am I doing this? You wanna lumfana, you say qalile ukubhema ke manje. Angazi sengibheme ini. Now we want the radius of the earth again. Remember when we determined our story there, we realized that the radius of the planet X is going to be the radius of the earth divided by 5. You understand, right? Right. So now what is that? What is the radius of the earth? It is 6,38 times 10 to the exponent 6 meters. So this is exponent 6. Maybe let's just write it nicely. Over, remember they said it's 5 times, so we divide that by 5 and then we square it. And we are good to go. Now we can just do our calculator gymnastics. Hey, when? Have you ever heard of such a thing? How sweet. It is indeed sweet. So this is 5,98 times 10 to the plus 24. Divide by 153. Or is it 153? Yeah, whatever that is, man. It is 8. 6,38. The exponent 6. Divide by 5. And then we square that thing. And then let's get our answer, guys. Our answer is 1,602 2 decimal places meters per second squared. And then what is the direction? Did they say magnitude? They just said acceleration due to gravity. So what is the acceleration due to gravity? Remember, acceleration is a vector quantity. Where are we? Yo, we just ran out of space. Yeah, wena. Okay. So what is that, guys? And then now we can say towards the center of planet X, because that is always directed to the center. So remember here, you will be caught out if you didn't write the direction, because you were not just told magnitude, they just said acceleration. So you have to think about it like that. Okay, how many marks were we supposed to get here? Well, 3 marks. Okay, not a big deal. Not a big deal. Usually for the formula, you are rewarded. I mean, they may give it to you the standard way, but usually there is a formula like this in your information sheet, but you have to make sure that when these substitutions, I don't know how to accommodate this. This is like a 4-mark question though, but we can just say, well, general substitution and the final answer. And if your final answer doesn't have a direction, you only get half a mark. Okay, so don't commit suicide. Last question. How does the gravitational constant G on planet X compare with that on the surface of the Earth? Write down greater than, less than, or equal to. And you already know, you guys, that it's going to be equal to, right? Because that is a constant. It does not change. It's a constant in the universe, so it is equal to. So we've sorted that question there. Let's go to question 3. Okay. Just get another color there so that we can have a bit of flavor. Now, we are told here stone X is projected vertically upwards. So this is projectile motion, right? From the ground with a speed of 3v. Okay, normally a sketch is an important issue. So you may want to say, well, there's my ground. When they don't provide a sketch, do yours. There's ball stone X. Then it's going to be projected upward and then it will come back down. Okay, so it's going to be there and then come back down. So that is stone X. Then we are told that the velocity or the speed here is 3v. Okay, I'm going to choose upward as positive. Right, it's always easier for me. The stone Y is also, okay, now there's another stone here. So there is stone y here. Okay, stone y will be projected and then comes back as well. There is the stone y. Okay, upward with a velocity v. So this guy here is just v. Then of course we're taking upward as positive for both scenarios. Let's just divide them so that we don't make an error of trying to mix the stories there. Okay, not a problem. So now we are told here, ignore the effects of a resistance. So what does that mean? We are having a closed system. All right, so we are having a situation like that of a vacuum where there's no other things but just gravity at play. Now define the term free fall. So how do we define the term free fall? So let's answer this question 3.1 quickly. A free fall, what is a free fall? Well, we can just say it's a motion of an object, okay, in which, okay, why am I shaking? In which, okay, in which what, mister? In which the only force acting is gravitational force. Okay, not a problem. So a free fall, it is a motion of an object in which the only force acting is gravitational force. Okay, that is it. Or you can say it is a motion of an object through which the object is accelerating due to gravity. So you can have plenty of ways. I'm just trying to simulate the exam, guys. Otherwise, I'm not really interested in writing this out because you already should know them. And if you don't, please, during your revision, you must make sure that you ensure you check these. And please use your exam guidelines a lot more than anything else at this point so that you are concise and to the point. Okay, so now that is fine. Now we're told stone X takes 10 seconds to return to the ground, meaning from here to here it is 10 seconds. All right. Now 3.2 says calculate the time taken by stone Y to return to the ground. 4 marks. Now how are we going to deal with this situation here? Well, we have to be a little bit crafty because the only relationship these two stones have is this guy, the V. So meaning if we can determine V here, if we can determine what this is, then we know that we will divide that by 3 to get here. Okay? And then we will know what this is, and therefore we can determine the time. So once you see a 4 marks type of a question there, you know already the 2 steps are involved. So let's get to the business. Do I have enough space? It looks like I've provided more than enough. Okay, let's just do this one here. Okay, what are you selecting now? So what is this answer? What is this question again? You know what? This resolution is good, but now my problem is that I don't see everything and I have to scroll up and down. I really hate that. Okay, that's 3.2. Okay, 3.2, we want to find out V. So we know that it takes 10 seconds to do it all. So what do we know? We can use the very basic falling body equation. So we can say the final velocity is equal to the initial velocity plus g delta t. Right? Because we know time, we know the final velocity, we know the initial velocity, and then of course what is important is the signs, because remember, as long as you are using these equations involve a vector, which is acceleration, so you cannot be careless about this. Now let's look at this one, guys. Upward we chose as positive, so this means this one is going to be negative 3v, so this is minus 3v because it is the velocity with which it hits the ground, but what was the velocity that it left the ground is the same, but it's positive, so it's going to be 3v plus, now this is minus 9,8 because this is always downward, so we chose up as positive, and then delta t we were told is 10 seconds. Now we can already see that we have to transpose that to this side, so we get minus 6v is equal to minus, so let's see, I think that's 98, so 10 times 9,8, it is of course 98. Therefore v, so it's going to be minus 98 divided by 6, which is 49,3. So this is essentially 16, now here it's very dangerous to kind of round off too soon, but I mean 3 is already 3, so it can't be anything, so we can just say 3. Yeah, maybe leave it to 433 dash dash, because this is an intermediate step. They didn't ask us that question, so we have to think about it. So how many of them? 1 2 3 4 5 6 7 8. Okay, 1 2 3 4 5 6 7 8. Okay, let's just do it like that. Okay, that is now meters per second, and you can already tell that this is positive, so it is upward. We can think about it like that, but if they said speed, it's a scalar quantity. Then we want to know how long will this one take to reach the ground. It will be a similar situation. So we can say now, therefore, the speed of stone y is going to be such that v is equal to, say this one, 16,33 16,33. Yeah, actually v, yeah man, what am I doing? It is like that. It is like that. Remember, we just wanted v here. We just wanted v and we found v, so we don't have to stress. And I think since we have v, we are where we want to be, so there's no need. There's no need. So we can say now for stone y, the situation is like this. Again, we do the same thing. Final velocity, initial velocity, plus g delta t. Now, what would be the initial velocity? Remember, it is v. So the final velocity is minus 16,33. I'm just going to leave that one because I think I'm just killing myself here. I think where needs be, we just do that. And then, of course, this one is also going to be the positive version of it, 16,33 plus minus 9,8 delta t. Therefore, our delta t is going to be equal to 2 into minus 16,33, right? Because when you transpose that, they add together. Divide by minus 9,8. So that should give us the time for stone y to return to ground. Yeah. So let's deal with this one quickly, guys. I think I'm taking too long now. 2 into 16, 33 divide by 9,8. So here I'm getting 3,33 seconds. Okay, so that is the time it will take our lovely stone. Stone Y to return to the ground. Okay, so do you see it took a little bit less time than the other stone? Okay guys, so that was 4 marks. So you can already tell 4-mark question, always know that you're going to have to do 2 steps. Okay, first of all, they may give you that to you and they will say here correct substitution and other things, but I think what is important is just getting that value. The correct substitution up there is not really quite a big deal, but it becomes more of a big deal here, and then the answer. Okay, we can't give you the formula again. No problem guys, we are doing a little bit fine so far. Now we are told here stone Y reaches a maximum height h. Okay, so what do we know here? We know that, well, our stone Y, so this maximum height of that stone is h, meaning from the bottom to the very highest point that it reached in its motion. Okay, and then now it says use an appropriate calculation to show that the height in terms of h that stone X reaches is 9 times that one of. Okay, not a problem guys, this is not a big deal, not a big deal at all. So this is 3.3, I guess. Okay, so let's keep moving guys. I don't want to waste too much time, but it looks like I'm going to be doing exactly that. So 3.3, we know, well, what is this height anyway? We know that, well, our h here, which is that for stone Y, is given by, okay, now, okay, let's just do this first. Maybe you will see it, but maybe you won't see it. I don't know. Let's just do this. Let's just say for stone Y, we know that the final velocity squared is equal to the initial velocity squared plus 2g delta y, right? Because this is vertical motion. But then we know that we want y, so we can say delta y is going to be our final velocity squared minus initial velocity squared divided by 2 into g. This therefore tells us that our h, which is that height they told us, the final velocity, remember at the highest point, it's always going to be 0. So we want that h. It's going to be h minus the initial velocity, we got 16.33, and then we're squaring that. Divide by 2 into minus 9.8. Okay, let's quickly do that. Then now we have this situation here of 16.33 squared divided by 9.8. Okay, maybe let's do this one. 9.8 times 2 so that we avoid issues. So what I'm getting here is basically 13,605 meters. Okay, so now look at that. Our h is that value, so don't round off too soon to too many. But if you take 4 decimals, then it's better, it's safer. Then we can say, now what about stone X? Well, for stone X, what do we know? We know again that the same situation, our delta Y there is going to be basically V final squared minus the initial velocity squared over 2 times g. Moving faster now. Then what is that? That is 0 squared minus, now this one, it is 16.33 multiplied by 3. Remember, that was 3 times v, okay? 3v. So it's going to be that one multiplied by 3 squared. Divide by 2 into minus 9,8. Okay, let's do that one quickly. Again, we're going to have 16, okay, let's put it inside the bracket. 16,33 times 3 squared. Divide by 2 times 9,8. So here I'm getting 122,4500. Okay, meters. And then now the last thing that we need to do, looks like the space is getting chowed. Now let's say we can say therefore, what were they saying? They are saying we need to show that now we need to show this calculation in terms of h. So we can say, well, we can say therefore delta y for our stone x is going to be 122,4500. Divide by that one, which is 13,6056. Let's see what that ratio is going to give us. So it's going to be 122,4500 divided by 13,6056. All right, guys. So to 2 decimal places, this is effectively 9h. Okay, because I'm getting 8,999. So to 2 decimal places, it falls away to 9, which is exactly what they want. So we've shown it. Okay, plenty of ways you can go about it, but this is the easiest and the simplest, I feel, should be able to give us those 5 marks, I guess. I mean, yeah. Usually here you will get, I think, a mark for that, and then a mark for this one to show that that is h. And then here we will get a mark for that particular thing, and then for a general substitution here, and then we get a mark for that answer. And wait a minute, how many marks do we have now? Yeah, we have 1, 2. Can't do that. So nope, one of the marks must just go. Okay, that one is the most important. So we are 3 marks rich now, and we can say fine, this one 4, and then of course for this ratio, because that answer was already provided, you just had to show it, that's all, meaning it has to be logically connected to where it comes from. Okay guys, hey, we're spending too much time now here and we need to move. Not a problem. So we are told here again, this is a famous question, velocity time graph, so you need to know how to do this. Sketch a velocity time graph for the entire motion of stone x. Okay, entire motion of stone x. Clearly show the values of the following on the graph: the initial, final velocities, the time taken when it reaches the maximum height. Easy stuff. Easy stuff, guys. No need to lose any marks here. So this is 3.4. So let's have a look here. 3.4. So I don't really have a ruler, so I'm just gonna do a rough sketch here. But when you do velocity time graphs, you need to be careful. You need the negative and the positive. Of course, this is the 0 mark, and then of course you have time in seconds, and then we know the entire motion is 10 seconds, right? Then halfway it was 5 seconds. It has to be, because the time it takes to reach the maximum height is the time it will take to descend to the ground again. Then now we need to find that velocity over there and this velocity down here when it reaches the ground. Now, what is that velocity? Of course, you say here velocity or speed. They said velocity. So this is velocity. How do I write this velocity here? So this is velocity in meters per second. Okay, and then of course we'll write the topic here. This is the velocity time graph of stone X. So don't forget, these things are mark worthy. The heading gives you a mark, the labeling of the X's gives you a mark, and everything that they required. So don't take it for granted. Now we want to know, what is this velocity? So what is that 16,33 times 3? Remember, that was times 3. So this is effectively 48,99. So I mean, we can leave that one there, or we can say 49. So I think 48,99 is much better. So that is 48,99, and then it's going to come back at minus 48,99. Okay, which you can round off to no decimal place when there's 2 nines there. So, but there's no specific rule that says you must do that. So all you know is that this thing is going to decelerate to the maximum height, which is going to be at 5 seconds, and then continue on its way down to hit the ground. But now here, be very careful to make sure that this indicates that this ends here. It has to be clear that this ends at that velocity, and it also ends at 10 seconds. So that is done. Okay guys, I think that is usually the tough questions in physics, where you have to do quite a lot over not so much of time. I mean, you know, things like that. So they wanted this time here, they wanted the initial velocity, they wanted the final velocity. But remember, this sketch is not going to be complete if you have not labeled. You don't have a topic or heading, you don't have the x's labeled correctly and their units there. You'll be killed. You will start crying. All right, let's quickly do this one. This is the easiest. Question 4. It's usually very quick, so no need to waste time here. Question 4 says, two objects A and B collide in a straight line on a frictionless surface. All right, so this is momentum, energy, impulse, and whatever. In the velocity versus time sketch graph below, the solid line represents the motion of object A. So there's a solid line for object A, and then that broken line is for object B. So that is important. Okay, let's look into the sketch. So we can see object A is moving at 4 meters per second, and then something happens, and then it ends up moving at 1 meter per second. And then object B was initially moving at minus 1 meters per second, and then something happened. It's all of a sudden moving at plus 3 meters per second. Okay, easy. Now we're told to define the term momentum. Again, guys, these are kind of easy marks. Let's see, do we have enough space? No. Okay, I didn't give myself quite enough, so let's write here. 4.1. So we know that momentum is defined as what? Okay, we can say it's a measurement. Okay, this chair likes to move. It's a measurement, okay, of what? Okay, of motion. Okay, which represents, okay, the product of what? Okay, of the mass and velocity of an object. Okay, so momentum is a measurement of motion which represents the product of the mass, okay, K is the mass, and velocity of an object. So it's as simple as that. You don't want to complicate that. And then they hit you with another easy one again. State the principle of conservation of linear momentum in words. Okay, So let's do it so that we can do our calculations over there. So 4.2. So we know that the law of conservation of momentum when a manson port kini of momentum iyantlwaela wa tseba ntho ena how e batla ho nsenyetsa jwale. So what do we know here? It states that the total linear momentum in an isolated system is constant. Okay, is constant in both magnitude and direction. Of course, these are extras. You don't really have to say them, but the magnitude as well as direction, it should be conserved or constant. But I think if you say it is conserved or is constant is fine. You don't really have to add this one. I will put it in parentheses to say that it's additional stuff, because this is also implied. In the MCQs, you may find this and then you start to feel like you washa ngwana ntate ka re wa fisa ngwana mafisa ya o tlo fisa he a tlo fisa maoto monna o ntse o robetse mane o ska nlela he hobane nkile ka o ruta ntho tsena ka o bontsha monna ne go bonisile shilo leswi a se ko dlaya. Ai, don't cry to me. Don't cry to me. I tried with words. I tried. Okay, enough talking nonsense here. Let's just get to this thing. Now it says, show by calculation, by means of a suitable calculation, that the ratio of the masses of the two objects, MA, see, they're giving us exactly the format of our ratio, that MA is to MB is this ratio right there. Okay, so this is easy. As I mean, you know that once we get to the story here, we know what to do. Okay, so all we know is that P before is equal to P after. Okay, start there. No issues here. Well, we're going to have here, this implies that the mass of object A multiplied by the velocity of object A plus the mass of object B multiplied by the velocity of object B. Those are the initial velocities, by the way. But yeah, I see now these things are terrible. Yeah, maybe let's just adjust that, because we will have a problem if we don't adjust that a little bit. So those are the initial velocities, okay? It's going to be equal to the mass of object A multiplied by the velocity, which is now the final of object A, plus the mass of object B multiplied by the final velocity of object B. Yeah, that is just the only annoying part of this. Now, what is the mass of object A? Well, we don't know. It's just mass of object A, okay? Multiplied by, what was the velocity there? The velocity, the initial was -1. So you read it from the graph. So you can say into -1 plus, again, we don't know the mass of object B. So it's going to be mB into, the initial was 4, right? Yes, it started out at 4 meters per second. Then we come here and say this is going to be MA into, now the final velocity is 3 meters per second. Yeah, what is that? No man. I am doing a crime here, you guys, and are quiet. Luna, letlamfumana. Kitolthola. Lefuna ukubolaya la coach. Kalbona with a cell phone like fee. Alright, so this is MB. Just made a bit of a meal of a situation there. So that is the story right there. So now this is basically telling us that we have here 4 MA minus MB is equal to MA plus 3 MB. Okay, great stuff. So we can already tell that, look, if you transpose this one to that side, it's going to be 3 MA is equal to, transpose this one to this side, it becomes 4 MB. All right, okay. And then of course here you do a mathematical gymnastic of dividing by MB. All right, and then here again we can do the same thing and divide by 3 and divide by 3. So MB cancels out, 3 cancels out. So guess what? We know now that the ratio of our mass of A over the mass of B when is equal to 4 over 3. Right. Therefore, MA is to MB is effectively 4 is to 3. Is it not what we are supposed to show? Definitely. So this one was a bit of a long question technically, guys, but not too long otherwise. Okay, so here you are getting how many marks? 4 marks. I mean, usually this is 5 marks, but it's fine. So you get a mark for that, correct substitution, and getting this situation over there. And I think presenting it the way they want is fine. Where's the extra mark? Is the gymnastics here? Perhaps. Yeah, I suppose so. Otherwise, I don't see, hey, when I'm giving extras. Hey, when Skabali, what you call? Don't be generous, mister. Now we're told here, draw a vector diagram. I like this, man. Reminding me of my metric here now, where we did vector diagrams, not these free body diagrams of yours. Anyway, there's nothing wrong with them. Draw a vector diagram. Vector diagrams, not to scale. Okay, to illustrate the relationship between the initial momentum and the final momentum and the change in momentum of object A. So we're going to look at object A, okay? As you can see, the initial momentum was quite big, right? And then the final momentum is small, isn't it? Because the velocity is actually the driving force, because the mass is constant. And then we want the change, which is what happened in between. All right, guys, so this is pretty easy. I mean, if you've done mathematics here, it's gonna be a walk in a park. But if maths is a bit of an issue, utlolla ngwana ntata, utlolla 4.4. Kanti kwenzeke ntoni apha ndiseno 4. This is 4.3, okay? All right. So, well, for object A, it is such that we know that we will have this situation here. This is the initial momentum, right? That is the initial momentum from this point, okay? I don't know what we can call that point. This is from this point and to that point. Remember, a vector diagram, there is a direction. Remember, momentum is a vector quantity. So this length represents its magnitude and then the direction, meaning positive direction, at least at this point. And then there was a bit of a situation. The final momentum was a bit small, right? The final momentum was a bit small, but still in the positive direction. So we're going to say, well, it changed into something like that, okay, from that same position. So this is going to be our final momentum, okay? Now the change is the in-between guy. The change, we're using the head to tail method, all right? So it is going to do that because remember we went that way, then we changed, and then that is how it goes. I hope I'm doing the right thing here, because if I don't do it this way, it's going to be painful, right? Because I mean, this has to be in that direction. So if we did that, we're going to have a bit of a situation. A change is something that always tries to oppose this, right? Yeah, man. I think so. So this is going to be change in momentum. Okay. Yeah, that is a very nice question, guys. And I think one to really consider, because things will get a bit hot if you don't remember these things. So we've done this thing with my student. There were some previous questions which had this thing. So I hope I'll have enough time to share them with you guys. Anyway, let me not talk too much. We want to run after this thing. And this question is effectively done. So it's 3 marks. Okay, so there's the initial, the final, and the change. Okay. All right. Okay. But is the change not smaller than this final one? Yeah, that is something else, man. I'm not sure. You just double check, but this is the idea. They said it's not drawn to scale, so it doesn't matter, but the picture explains our story. Okay, let's get to question 5. Now, once we get to this one, I can go. What are you doing? Okay, guys, hey, I'm taking forever now, and I'm making mistakes too. All right, let's just get to this diagram. Work energy theorem, which you already know how to do, so we're just gonna drill it and move on. A 10 kilogram block, so what is the mass? Is 10 kgs, is sliding along a rough surface. The portion of the surface AB is inclined at 35 degrees. So the angle is important to the horizontal as shown in the diagram. Okay, so meaning there is friction here. This surface is all friction, okay? All of it. Okay, so, sorry, now it says the block reaches point A at a speed of 8.84 meters per second. It slides up the incline and comes to rest at point B. So at point B, if it comes to rest, we know that the velocity at B is 0 meters per second. So that is the most important part. Okay, not a big deal. Now we are told here a constant frictional force of, okay, they're giving us that value of 45 newtons acts on the block as it moves from A to B. So friction always opposes motion, because now the direction of motion is that one. So we're going to choose the direction up slope as positive. So it is very important to do that. Now again, free marks. State the work energy theorem in words. Can I just try and save time now, guys? Work, okay, yeah, maybe let's not. Why do I want to take shortcuts? I've decided I'm gonna go the long cut, so let's do it. 5.1. So we have work energy theorem. It states that the total work done on an object is equal to the change in the object's kinetic energy. Hi, le tla ntshwarela he ka di writing tse jwang jwang mona. Hai, ha kena taba le nna jwang. Now, we are told that is easy, my friend. Don't lose marks there. Use the energy principles only to calculate the distance x. Okay? Now, you can use any of the energy principles that you like shown in the diagram. So that is fine. Now, what I like to do here is a free body diagram or a body diagram. So if we have our box here, we will have a few forces doing their thing here. First of all, we will have the weight straight down, and then the weight will resolve to its components to some extent, which is going to be Fg parallel, and it's going to also give us Fg perpendicular. Okay, they do like that, so that's gonna be Fg, Fg perpendicular, and then that is Fg parallel, which we can also put there. So this angle comes here. Okay, that angle and that angle are the same. And there's another force here, which is going to be the normal force. Okay, normal force is basically equal to Fg perpendicular. And then of course there's an extra force now, which is that of friction. So there is friction, but this one, because we're in motion, it's Fk. It's kinetic friction. Okay, so we need to think about that when we do our calculation. So how many forces are acting parallel to the direction of motion? It is this guy and that guy, and they're acting in the same direction. So these are the only two forces that are working together. So the resultant force is the addition of these two, and that will stop this object at point B. So we are sorted. So while we are sorted, then we're going to say, fine, we know that W net is equal to the change in that is the energy principle that is immediate at this point. Maybe I should when ingathi spaces zizamshiya nje. I don't want to be left behind. Okay, so let's just do it. Let's carry on. So what are the forces that are here? It is the sum of the frictional force Fk plus the what you call Fg parallel, ne? And what is that? Times delta x, which is what we want, and then cos theta is equal to half m, the final velocity minus initial velocity squared. So this is exactly how you go about this business here, guys, and then we keep going. What is the frictional force? They said it's 45 newtons, but remember, it is going the other way down. So I mean, these ones you can just add because you don't have to worry about the direction. This cos theta will take care of the problem. So we have 45 here plus the mass here is 10 times 9,8, which is the, parallel is going to be sine of 35 degrees. That is the incline, okay? And then times delta x. Now cos, remember this is opposing, these forces are opposing the direction of motion. Cos of 180 degrees is equal to half of 10 into the final is 0 squared minus the initial is 8, what was that? 8,84. Okay, that one is squared. Okay, guys. Yeah, these calculations are really seriously doing a number on me right now. So we can say here, therefore, our delta x is going to be equal to, now cos of 180 is a negative, is going to be equal to half of 10 is 5 into minus 8,84 squared, divide by that sum, but that sum is negative because of this cos of 180. Okay, now we can say 45 plus 10 times 9,8 times sine of 35 degrees. All right, guys, so we have our distance right there, so we've got to move. I think here I kind of relaxed a bit, but it's no trouble. We have 5 into 8, comma 84 squared, divide by 45 plus, now we have a situation here of 10 times 9,8 times sine of 35. Yo, sizoba nengxaki la. Okay, I'm getting 3,86 meters. I think that is the best I can get at this point. I don't even want to explore other options. We are almost losing time, but I mean, if we're on question 5 already, I'm happy because we can enjoy the last hour doing the easy questions. Yeah, so it's not too bad. Okay, guys. So that is exactly that. So you always get a mark for this. And then we get a mark for some situations that really matter. I think this one is important. And those 2 marks are important. And then this sum here is worth a mark. Ne? And then this situation also is, I think, how many marks there? 4. Sorry, so that is 3 marks already. So let's just say this whole left hand side, the correct substitution in there, and then the correct substitution in there. That's basically where the 4 marks come from. Okay, not a big deal, guys. Easy stuff here. Now we are told here, at point B, the block only just manages to remain at rest, meaning it stops and it doesn't slide back down. Okay, meaning now the friction of the surface is exactly perfectly balanced with the FG parallel, because if they were not perfectly balanced, that would mean this FG parallel would pull it down against friction if friction was smaller. So if this stops, it means the FG parallel is exactly equal to our frictional force, because this time friction is going to act against FG parallel when it stops at point B. So we are told to draw a labeled free body diagram when it is at point B. Okay, that was 5.3. Okay, 5.3. So the free body diagram here is this one. So what is going to be that friction? When it stops, it becomes static friction, okay? And then we're going to have FG parallel here. And then we're going to have still the normal force there. And then we're going to have our FG perpendicular. But if you like, you can have our frictional static friction. We have our normal force, which must be perpendicular, right? And then you can have our weight, which is FG. So maybe this one is more simplistic, maybe the favorite, but that one is also okay. But for these two, you will get a mark and then a mark for the normal force and the frictional force. Easy stuff. Next, we are told calculate the magnitude of the frictional force acting on the block at point B. All right. So we want the magnitude now of the frictional force. Well, I kind of lied. Remember, that was Fk. So this is not exactly equal, but it's the same idea, but not exactly equal to this one. Kinetic friction was smaller because it allowed motion, but static friction is a bit bigger than that. Ne? Now let's see. What is this question trying to establish? Look, if we resolve this into 2 forces acting in the horizontal plane, when this body stops, we have our static friction and we have our FG parallel. So meaning for this to stop, these ones must be equal. So what do? We can just simply say here the resultant force, Newton's second law, is equal to ma. And since there's no acceleration, this is going to be 0. So we know that our frictional force minus Fg parallel is going to be equal to 0. Okay, we are sorted. So we can say therefore our frictional force, which is the static friction, is going to be exactly equal to Fg parallel. And how do we do Fg parallel there? It's going to be 10 multiplied by 9,8 multiplied by sine of 35, because it is still the same incline. The incline doesn't change. So it's still the same 35 degrees. So let's find this one out. Okay, so this is 10 times 9,8, which is 98, times sine of 35 degrees. So I'm getting here a 56,21 newtons. Now this is going to be upslope. Again, that is not really necessary at this point because they said magnitude. So when you're told to do the magnitude, you just do the magnitude, but please be in the habit of treating vectors with respect, okay? Even if it's not going to give you a mark, but it's a good thing to keep in mind, because when it's necessary, you won't fall short. All right, so this is a standard 3-mark question. That, correct substitution, and the answer. 3 marks in the bag. Is there anything else? The answer is no. So we move on. So at least I think, guys, we're able to keep a bit of time. So let's trace this question down. Question 6 says a siren of a stationary police car. How is this car? Stationary. Emits sound with frequency of 300 hertz. Okay. The speed of the sound in air is 340 meters per second. Okay, not a problem. Again, easy marks. State the Doppler effect in words. So this is 6.1. So we know that the Doppler effect is defined as a phenomenon. Okay, it's a phenomenon. Let me try and put the words nicely. You know, sometimes it's easy to just mess up. Okay, we're going to say it's a phenomenon of okay, let's just say it's a phenomenon whereby electrons are ejected from a metal surface as observed when light of sufficient energy is shown to the metal surface. Okay, I mean, you can put it in as many ways as you want, but the essence is you're taking a light of some sufficient energy, you're shining it onto a metal surface, and electrons are ejected. So you make sure though you don't lose the science there in whatever words you can create. We were told use your own words, so that's why I'm able to just sing as much as I want. Try to use some technical terms like phenomenon. What is that? It's English, Papa. Yes. Okay, calculate the average length. Sorry, calculate the wavelength of the sound waves. 3 marks, which is easy, right? So 6.2, it's a very simple question. So basically, we know we take it from V is equal to frequency multiplied by lambda. Why is my lambda trying to look funny now? Alright, so what do we want? We want the wavelength. So this implies that our lambda is going to be v over f. Our velocity is 340, or speed. Frequency, we got 300 hertz, right? Right. So let's deal with this wavelength and find it in meters. So we have 340 divided by 300. So we're getting something like 1,13 meters. Remember, when they say calculate to 2 decimal places is minimum, but even if you left 4 decimal places, remember when they say at least, it means that's a minimum. It's either that or more. So if you put more, it's still okay. No one is going to punish you. So this one, formula, substitution, answer. No questions about it. Now it says, write down one application of the Doppler effect in the medical field. Are you all going to become doctors? Well, who cares? 6.3, you just have to know. So we can use this in the medical field, as a Doppler ultrasound. But don't write like that. Just write the full word. Doppler ultrasound used to measure blood flow. Okay? In blood vessels. But I mean, if you just stop there, it's good. That's what a Doppler effect is used for. Okay? Yeah, that is it. That is it. And then, of course, they can use ultrasound to listen to the heart and things like that, but mainly for the heartbeat, okay, because the rest is not really using the Doppler effect. Okay, not a problem, guys. Let's move on. What is the story again? Now it says the police car moves at 30 meters per second between two stationary observers, A and B, with its siren on as shown in the diagram. So I guess since we are still under question 6, that statement was essentially for question 6. So we will just put it to our minds that we're still having that situation still applying. Okay, so now we are told to calculate the wavelength of the sound as perceived or heard by observer B. Okay, remember now the direction of motion is towards B, so B will hear a much higher frequency than is emitted. And then of course it's a 4-mark question, so 2 steps are quite a decent thought there. So let's do 6.4, and then we do 6. No, when I'm on 6.4.1. Okay, guys, so all we know is that, well, frequency of the listener is equal to the velocity of, the sound in the medium plus or minus the velocity of the listener over velocity in the medium plus or minus the velocity of the source multiplied by the frequency of the source. So this is the Doppler effect equation. There is no question about it. So we want to find out what frequency is this listener going to have. So this is basically 340. Now the listener is stationary, so we don't even think about what to do there. It's 0. And then now we come to here. This is the velocity of 340. And then the question is, do we say plus or minus? Remember, this thing is moving towards, so it's going to hear more. So that means, in a nutshell, this one must be a minus. Okay, minus, what was the speed of this thing? It's 30 meters per second. So we're going to say minus 30. Please, guys, this is the tricky part. Always think about this part here. It's quite important. And then the source was emitting 300 hertz. So we can just simply do that calculation quickly. So we have here 340 by 300 divide by 340 minus 30. And then what we get here, we get 329,0322 hertz. Okay, this is great. Now you can already tell that this is higher than the emitted frequency, so it makes sense. Otherwise, if you get a smaller frequency than the emitted frequency, then you know that, well, you must have done a mistake. So you have a lot of things to aid you in making sure that these two things don't look alike. They must not be alike. Okay, so you see, rounded off to the nearest, it is 329 compared to 300. So you see, we're hearing more than was actually emitted, so it makes sense. We can say therefore the wavelength that is heard is going to be equal to the velocity of sound in air divided by the frequency that is heard. So the velocity is 340 divided by what is this frequency, 329,0322, which is going to be equal to, so we quickly do that, 340 divided by 329,0322, and then we are getting a wavelength of 1,03 meters. Of course, the final answer, because remember that was an intermediate step, so you don't want to really carefully take it down to 2, but here you can, but you can still leave it more. It's up to you. When they say this or more, you can do as you please. So 2 steps, guys, 2 steps. So obviously for the primary equation, it's quite important, and then getting this one is important. Then the correct substitution here, and the final answer gives us those 4 marks on offer. And then now we have to calculate the frequency perceived by A. So this one is moving away, so we're supposed to hear less. So let's do it. So easy again, simple Doppler effect question here. So we have 6.4 heaven 0.2. So again, the frequency of the listener is going to be equal to again, Doppler effect equation, right? Yeah, man. Yes, this thing is long, but getting a bit tired. But yeah, you can't cry, guys. You just have to put the fight until it's over, ne? If you start making excuses for yourselves, you're just going to cause yourselves unnecessary problems. Okay, so this is 340. Again, there's 0 there because that listener is stationary. And then it's going to be 340. Remember now, this is moving away. We're going to put a plus there. A 30. Into, what is this? That was 300. What am I trying to do? So again, it's the same 2-step approach, folks. So we have 340 times 300 divide by 340 plus 30. So I'm getting 275,6757. At least you can leave it at that, hertz. Okay, that is the frequency, and you can already tell that, look, this frequency here compared to that one is less, and it makes sense because that thing is moving away from the listener. So we want the wavelength. So we can say now, therefore the what is this? Therefore the wavelength of the listener is going to be equal to, let's just go ahead here and not waste time, over 275,6 757. So we don't want to waste any more time. So divide by 275,657. 6757, and then I'm also getting here a 1,23 meters, which is the answer. Okay, so what is the story here? So I mean, yeah, I don't know. Usually here, because I mean this is a sub question of another sub question, I mean within the same question. So technically here I would simply say you're getting a mark for a correct answer here. You're getting a mark for the substitution in that final answer, because this time they wanted us to do a wavelength. Okay, no problem. And then now we are told here the police car stops when its siren the police car stops with its siren on, and observer B moves away from it. Okay, so meaning, let's just say it stops right here, and then this one starts moving away. If this one moves away, this one will hear less of what is emitted. So maybe it's a question on that. So now it says, is the frequency of the sound that observer B hears greater than? Remember, frequency of the sound that B hears. B is moving away, so they will hear less. Okay, it is going to be less than. So we've sorted that one. So it can't be equal to, it can't be greater than, because B is now moving away. So it's going to be less than. All right. So question 6, effectively done. So guys, easy marks. See, I left a lot of space here thinking I'm going to need it. So I didn't. So do you see, you guys can cruise if you can, but yeah, let's just not talk too much at this point and just keep moving. Question 7 says, an investigation is conducted with pairs of identical point charges. Now, in electrostatics, when you hear that word identical, we mean equal masses and then the spherical volume. Okay? And not, should I say, the sign and magnitude of charges. Okay, so if they don't talk about the magnitude of charges, no, even magnitude, what am I saying? Don't lie, Makamba. You're starting to lie to these kids now. Ish. So when we say identical, we mean equal masses, equal coulombs, as in charge. That is just the magnitude of the charge. And then, of course, spherical volume. Not signs. Be careful. If signs are not said as such, that's your nota bene. You need to make sure that the signs, if nothing is stated about them, it is not implied in that identical. Identical means mass, the coulombs, meaning the charges, the magnitude of the charge, but not the sign of the charge. Of course, the spherical volume will be the same as well. Okay, now an investigation is conducted with pairs of identical point charges, all placed distance r meters from each other. So all of them, they have this distance as shown in the diagram. So there it is. So we have our distance r meters there. Okay, now we are told here the relationship below shows the graph below shows the relationship between the electrostatic force F exerted by one point charge on the other and the product of the two charges, which is Q2. Of course, the magnitude is the same. That is why we're getting a Q squared. Maybe let me just shade it like that. Yeah. Okay, if you can see here, this is a straight line from the origin like that. So this is a direct proportion. Okay, great. Now, it says for this investigation, write down the controlled variable. So we have 7.1.1. Of course, it is the distance. R between the point charges. Okay, I don't know why is that bracket coming. It should be a full stop. Okay, that is the controlled variable because we kept it the same throughout. Then it says write down the relationship between the electrostatic force and the product of the 2-point charges, which is the q squared. Well, this is 7.1.2. We can say the force F is, in fact, you can even write it in symbols. They didn't say write it in words. Yeah, man, you can say there's a direct proportion. You just do that. Why must you suffer? It's just 1 mark, okay? But you can even say in words directly proportional if you want. Okay, it's directly proportional to the product of the charges. So it's done. 1 mark. Calculate the gradient of the graph. Thankfully, it's a straight line, so we don't have a least squares regression line of some kind here. That is terrible. So here you can take any of those points. You can see there that the gradient is going to be 1 because it's 1:1, 2:2. You have 3:3, 4:4. But of course, you're using the dots. So you're going to be using these points. Any of the 2 points that you want, you can do that. Okay, so we can decide we're going to take, say, 1 and 3. Okay, we want the gradient. Where is that question? 7.1.3. Okay, we have 7.1.3. So we can just say the gradient, or even in words, it's going to be equal to change in the force over change in the q squared, right? Because that is the change in x over change in y. So if we look at this one, if we choose that 3, there's going to be 3 minus 1. Okay. So you can just take any 2 points, 3 minus 1 over. So this is going to be 3 minus 1 as well. Okay, great stuff. And then what is that? So this is basically 2 over 2, which is 1. But now remember, this one is times 10 to the exponent minus what? 12. Because here there's nothing here. They didn't tell us that this is what, coulombs or what. So it's just 1, or it is 1 times 10 to the minus 12. Am I right or am I wrong? Sometimes things happen. Things happen, Baba. Yo. Things happen, my brother. So I think that is important though, because it is times 10 to the 12. So let's just write it here, times 10 to the 12. Okay. But a gradient, remember, it's a ratio, so there will be no unit. Okay, guys, we found the gradient. Let's quit wasting time. Now we are told here, use the answer in question 7.1.3 to calculate the distance r between the charges. Okay, not a problem. So this is 7.1.4. So anyway, we know the electrostatic force from Coulomb's constant is K, Q, say 1, Q2 over R squared. So that means this is what we do. But now if we're going to use this gradient, which charge do we choose? Now this becomes a bit of a situation. So, well, these fall on the line. I don't know if it is safe to use them, but let's just be crafty about it. If we are smart, we will be doing things like this, because if we have to use this gradient, I think this information though is already telling us that we can't use any charges, by the way. It's going to be dangerous. So if we have to use this gradient, look at this, it's force over charge squared. Now how can we do that? Because we know that these two effectively gave us K times Q squared, right? because they were identical, even though the signs may not be the same, over r squared. So all we do is, if we cross multiply that, or we simply divide by q squared, maybe let's just put that word, maybe to say cross multiply would be dangerous. If we say this thing divide by q squared, we will say divide by q squared, and then that q squared takes that one out, and then we end up with f over q squared equals k over r squared. Now this is much better because we know this is a constant, and guess what? This expression is the same as that expression, isn't it? And what did we get? We got 1 times 10 to the 12. So we can just simply substitute that one and say 1 times 10 to the 12 is equal to k is 9 times 10 to the 9, and then over r squared. Of course, this is over 1. And what we want to do is to cross multiply this time around, and then we're going to have here aibo. Therefore, r squared is going to be equal to the square root. Okay, I'm just moving quick, guys, of 9 times 10 to the 9 divide by 1 times 10 to the 12. Okay, let's deal with the r then. What is the r? Did I write r squared? Ish, this guy. Okay, I think I'm losing focus a little bit. Okay, let's do it. The square root of that ratio 9 to the 9 divided by 1 to the 12. So I'm getting something like 0, 0, 0.9. This one, I can't discard that 4 because there's an 8 before it, so it's going to be 9.5 meters. Remember, they say 2 or 3 or 5 or whatever, so it can't be less than 2 decimal places. So I think I can't discard that 4 because it has a bigger number before it, so you can't just throw it away. Or you can decide that you take the 1 here and put it here, so it becomes a 1, 0, 0.10. So that's what it is. Okay, guys, so this is that. How many marks was that? 4 marks. Okay, so that's fine. I think here always Coulomb's constant, I mean, we do the same thing. I mean, Coulomb's equation, or whatever you call that, Coulomb's law. Yeah, Coulomb's law, basically. But I don't know, man. How many marks there? Here went 4. All right. I think though this gymnastic here is quite interessante. It's interessante writings. And then the rest we can just say substitution and the answer. This final gymnastic is not really a key point. So there's our 4 marks, guys. And we move on to the next portion of this question. Quickly, 2-point charges Q1, which is plus 8 microcoulombs. So this is plus 8 microcoulombs is 8 times 10 to the minus 6 coulombs. And then Q2 is plus 2, so we're going to have a plus 2 times 10 to the minus 6 coulombs. Are separated by a distance of 0.4 meters as shown. Okay, fine. We can see that. And then we know that now there's that point P, which we don't know about. Okay, let's forget about it. Describe what an electric field is. Okay, easy marks again. 7.2.1. So an electric field is described. How do we describe an electric field? Well, we describe it by saying it is a region, okay, in the space around the charge, any charge for that matter. So it is a region in the space around the charge, okay, in which an electric charge. Sometimes they say a positive charge, whatever. So in which an electric charge or a positive charge, okay, will experience an electrostatic force. Okay, I mean, you can say it is an electrostatic force per unit charge. It's still okay. But when they say describe, it means, get into the habit of getting into the question. What does the question say? A description is not just purely, a definition. So you want to also portray the ability to understand what is being asked. So I just wanted to put my light on. You see this power cut? It's getting on my nerves, but what can I do? It's not only me who hates it, we all hate it. Okay, not a problem, guys. So I think we've done our description okay. As long as there's electrostatic force somewhere, okay? And then an electric charge, be it a positive or negative charge, doesn't matter anymore. But of course, the earlier experiments, they used a positive charge. So that is why the positive charge features. But it doesn't mean it's the only one that does so. All right, not a problem. Yeah, that is it. Let's do the next one. We are told now the net electric field at point P is 0. Okay. Now calculate the distance d between point P and point charge Q. Okay. Calculate the distance between point P and the point charge Q2. Okay, that d there as shown in the diagram. All right, so this is again a question that may be a bit hectic, okay, but I'll try to combine it. It's very nice. It's very nice. 7.2.2. So we know that, well, E net is going to be equal to, how do we deal with this one? It's going to be K Q2 over R squared. Remember now, these ones are vectors, so that one is going that way, the other one is going that way. So they will effectively cancel out. So it's going to be this one minus KQ1 over R squared, okay? That is the essence of the story here. So this implies that 0 is equal to, and then we look at this one. What is K? K, do we really want to worry too much about other things? Not at this point. Let's just forget it. So this is K, Q2, because Q2 is effectively Q, okay, no, let's not lie. Q2 over, but now what is the R? It's D for Q2, so it's just D all squared. In fact, why do I even have to put it inside brackets? We don't want to waste time here. K times Q1 over, but now Q1 is what? Is 0,4 minus D, because it is that distance there. And then that is squared. And then, of course, at this juncture, you can just transpose the other one to this side. So, I mean, we can divide by K to eliminate K. So whatever you do, it becomes 0. So we have 0 is equal to Q2 over D squared minus Q1 over 0,4 minus D, that squared, okay? Okay, all right. Now we can transpose the other one, say Q1 over 0,4 minus D, that is squared, equals Q2 over D squared. Okay, not a problem. Hey, do I have enough space here? Is this the last question before I start messing around? Yo, because now I'm getting too comfortable here doing nothing. Now let's look, what is Q1? Q1 was 8 times 10 to the exponent minus 6 over 0, 4 minus d, that is squared, which is going to be, that one was, I forgot, is it 2? Yeah. So this is 2 times 10 to the minus 6 over d squared. Of course, there's a lot of squares here. You can just take the square root sign here to avoid a quadratic. But be comfortable doing it. There are times where you can't avoid it. Okay, let's just cut the corners at this point. But be careful of rounding off, because that's another nasty situation that's going to come up here. So let's see, square root of 8 times 10 to the minus 6 is what? So it is 2, 8, 2, 8, 4. We can throw the rest away. Times 10. I work 10, we'll just get a few parallel writing. Times 10 to the minus 3 over, that one remains now, 0, 4 minus d equals, let's do the square root of 2 to the minus 6 is 1, 4, 1, 4. We can get rid of the rest, times 10 to the minus 3 over the square root of d squared is just d. Okay, at this point we just do cross multiplication, and what is nice about it is that we're going to have here d into yeah, this thing is gonna be hectic, you know. Okay, so let's just not be silly here. So we're going to have here 2, 8,284 times 10 to the minus 3d. Okay, we cross multiplying, equals, and then when we multiply the 0, 4, so it's going to be 0, 4 times 1, 4, 1, 4 to the exponent minus 3 times 10 to the exponent minus 3. So I'm getting 5,656 times 10 to the exponent minus 4. Minus, this is 1,414 times 10 to the exponent what at d. It's going to be like that. So we are essentially sorted. So now we have like terms, so we transpose this one to that side. So what we're going to have here, we'll transpose this, so we're going to have 2,8284 times 10 to the minus 3 plus 1,414 times 10 to the exponent minus 3 is equal to 5,656 times 10 to the exponent minus 4. All right, yeah. I have a fit. Clasher is the enemy. Now this is the common factor. So I'm gonna move quick now. This is the common factor here, and we essentially are going to isolate it. So we can say here safely, therefore d is going to be 5,656 times 10 to the exponent minus 4 divide by divide by the sum of these two. So it's going to be 2,8284 times 10 to the minus 3 plus 1,414 times 10 to the exponent minus 3. Okay, yeah, this was a bit of a hectic calculation. Divide by that 2,8284 x times 10 to the exponent minus 3 plus 1,414 times 10 to the exponent minus 3. Yeah. So I'm getting 0,13 meters to 2 decimal places. So it's just one of those annoying equations, because yeah, there's a lot to consider, but I kind of prolonged things. So please guys, be in the habit of trying to narrow all of these unnecessary steps at times as quickly as possible. No one is going to ask you what happened. This is physical science, but remember, don't skip too many steps that are important. So let's not even go into where the marks are. I just hope the answer is correct. If it is not, you'll let me know. Let's look at this one. Now the 2-point charge is allowed to touch and return to their original positions. Calculate the number of electrons transferred upon contact. Again, 4 marks, that means 2 steps again. Alright, 7.2.3. First of all, we can see that the new charge is going to be Q1 plus Q2 divided by 2. That was 2, was it 2 now? It was 8 times 10 to the minus 6 plus 2 times 10 to the minus 6 divided by 2, which is what? Let's find out. 8 times 10 to the minus 6 plus 2 times 10 to the minus 6 divided by 2. Remember, it's an average between those two charges. So this is 5 times 10 to the exponent minus 6 coulombs. Okay, great. That is microcoulombs. Therefore, the number of electrons is going to be the charge over the charge on an electron, which is 5 times 10 to the minus 6 divided by, is it 1,66? Hi, gosh, here. Where's the information sheet? The charge on an electron is 1,6, man, not 66. 1,6 times 10 to the minus 19 coulombs. Then this gives us the number of electrons. Let's just try, guys, to move. I feel like I have wasted too much time. So we have here 3,13 times 10 to the 13 electrons. Okay, that is quite a number of them, ne? Yeah, that is quite a number of them. Again, this was a 4-mark question, so I guess that is important in this one, and then this substitution in the answer. So this is how you crack question 7. Let's quickly run through question 8. Question 8 is electric circuits. You see, this is like Newton's laws of motion in electricity. It's hectic. In the circuit below, an unknown resistor X, okay, unknown, is connected to a 10 ohm resistor and a 12 ohm light bulb. Okay, this combination is connected to a battery with an internal resistance of 2 ohms. Now, the resistance of the connecting wires and the ammeter may be ignored. Okay, fine, always is the case. So is all of what we have up there? Yeah, it's all written in. Of course, this one is 2. They just wrote R in there. Okay, it's 2 ohms. Okay, not a problem. Now, we are told here when switch S is closed, okay, meaning the circuit is completed, the voltmeter reading decreases from 24 to 21,6. So that tells us this is the EMF and this is our external voltage. All right, so it says now write down the term used to describe 24 volts. Okay, it is the electromotive force. Electromotive force, which is what we call EMF. Okay, but they said write down the term. The term is electromotive force. Okay, in short, EMF. All right, calculate the reading on the ammeter. Where is the ammeter? The ammeter is that segment. Remember, charge will flow from the positive terminal through the circuit, and then when it gets here, it splits into that portion and that portion. So this A1 is basically this portion that passes through the 10 ohm resistor. Okay. All right. Okay. So what are we going to do about this one? We don't know the charge there. So it's going to be a bit of a situation, eh? Yeah, it's gonna be a bit of a situation. How many marks is this? 5 marks. Okay. We have a bit of work here to do, so let's just do it. Let's just do it. How are we going to plan it? We know the external voltage is that. So we need to do ourselves a favor here. Yeah, this question is quite hectic. There is no one single way. You're just gonna have to do probably 2 steps here or 3. At times when it's 5 marks, you may need even 3 steps. Okay, just trying to think about it a little bit. So if we can find the voltage across these two, right, the voltage across these two plus this one should give us that. So meaning if we take this voltage and take out that, it's going to be the voltage across that, and then yeah, it's going to be easy. It's going to be easy. For a moment I wanted to kind of cry, but thank God I am not a crybaby. 8.2. I'm more of a brave and crazy individual, but yeah, sometimes I get caught out. Okay, so how we're going to answer 2.1, we can say here the V parallel, we're just going to write it. V parallel is going to be equal to the V external minus the V across the 12 ohm bulb. Okay, maybe let's just say VB to suggest the bulb. Okay, this is going to be 21,6 minus, now what is this one? Hey wena man, hey wena, hey wena, hey wena. It's not as easy as I thought. No. What is going on? Yo, this question, let me just do it this way. No, man. A1. Can we use the EMF? We need the total current first of all. And the total current, we can find it from the internal resistance. Okay, so we can just say here, V lost volts is going to be equal to the total current multiplied by the internal resistance. That is what we know. And then we know that this implies that our I tot is going to be this lost volts. Lost volts is going to be the EMF, which is 24 minus 21,6. Yes. And then over the internal resistance, which is 2. So we move as quickly as we can. Otherwise, yeah, it's not good. 24 minus 21,6 divided by 2. So I'm getting a 1,2 amperes. Okay, that is an intermediate step. So I have found the total current, meaning the current that is going to split into these two. Why do I want that current? Because I want this voltmeter right here. I want this voltmeter. So it will help me a lot. Now let's see. This implies that V parallel is going to be V external minus VB. All right. Which is important, right? V external is 21,6 minus the VB is going to be IR, right? Which is 1,2 multiplied by 12. Because the light bulb is 12, right? Yeah, maniac. E batla ho mpolaya, e nahana hore ke mang. E tla bolaya mang. I'm not the dying type. I don't respond very well to threats. Eish. Pomporo le bona. Hai. Varieteta momish. So this is 7.2 volts. So guys, once we know V parallel, we can say therefore the ammeter there is going to be equal to V parallel over the 10 ohm resistor. So let's just not even cause ourselves unnecessary formulae that are 100. So it's going to be 7,2. Remember, V parallel is the same for both resistors. Divide by the resistance now is 10. Yeah, almost made a meal there. So we have 7,2 divided by 10. So this one is 0,72 amperes. All right, not a problem. So guys, we are doing a bit fine, but time is really chowing us because yeah, we talked and talked, but yeah, I tried to keep it to a minimum though. I hope I did not irritate anybody. So you can see there's a lot of steps here. First of all, the lost volts is important to determine and is important to get that answer, right? Right. And then that is 2 marks. And then this is important to get 3 marks. And then we can say substitution there and the answer. You may not really get for the formulae. They are pretty simple. So when you have multiple steps, the formulas may not necessarily get the marks for you. Okay, guys. Easy stuff. Not really too technical. Now 8.2.2, calculate the resistance of resistor X. Okay. So 8.2.2. So we know that, well, the resistor X is going to be V parallel over I. Yeah, but we can just say, I don't know, what are we going to say? It's going to be I2, maybe I2. Yeah, maybe let's, you know what, let's just not cause ourselves issues at this point. Yeah, maybe we can say I2. Yeah, doch. Yeah, this is horrible. What is V parallel? We got 7.2, ne? Yeah. Then now we're just going to try and be fancy about it. What is I2? I2 is going to be the total, which is 1,2 minus the other one, which is 0,72, ne? So you guys need to be very quick with these kind of things. You don't want to end up with too many useless steps that don't really help. So you want to move as fast as you can when you can. 0,72. So make sure you don't delay this thing. So I'm getting here 15 ohms. Okay, so that should be fine. That should be fine. All right. How many marks were they giving for this one? 4 marks. Yeah, when? Why is it 4 marks now? Hubaning. I mean, the total current, we got 1.2, right? 1.2. Say minus 0,72 is 0,48. So that is that current. And then say 7,2 divided by 0,48. Yeah, it's 15. Okay, I accept. I accept that would be the resistance, because remember these two are in parallel, so it should be something like that. 15 ohms, no problems. Let's keep moving, guys. If you spot an issue, you let me know. Right now it's injury time. This is when you just keep moving. Now we're told you calculate the rate at which energy is dissipated in the light bulb. Okay, so easy. So this is 8.3. 8.3, maybe let's use the space. I mean, I think I gave myself a lot of space here. Sometimes I doubt how easy it is to work through this. Look like an entire page. Maybe let's dig here. 8.3. So we want the power. Basically, the rate at which energy is dissipated is power. So it's going to be I squared R. What is the I? Is 1,2 squared multiplied by R, which is 12. This one is straightforward. 1,2. Remember, that was the total current that we calculated times the 12. The light bulb was at 12. So this is 17,28 watts. That is the rate at which energy is dissipated there. So I'm wondering though, by the light bulb, Hewen, yeah man, this one gets the total current. This one gets the total current, so yeah, that should be correct. That should be correct. So I don't know why they're giving 4 marks. Maybe because of this square and then the general substitution, the answer and the formula. Yeah, maybe that's where the marks come from. All right, so let's do the last question here now. It says, how would the brightness of the bulb change? Okay, what are we looking for? The brightness of the bulb change if resistor X bends out. So remember, if this one bends out, this is like an open switch. Okay, so when this bends out, it's like you're opening a switch here. So this creates a high resistance, which means an infinite resistance here. So that's no current that's going to pass there. So the current now comes through this part. Okay, so which is the complete circuit. So this basically means we will effectively increase our total resistance, because remember, this V parallel or R parallel drops the total resistance effectively. So now if we lose this one, then these are going to be in series. So in series, they will have an increased total resistance in the external circuit. If that happens, with the EMF and the internal resistance being constant, the issue is that the current is going to be increased. No, I'm lying. Increased resistance, the current will decrease. Okay, and if the current decreases, this brightness will drop. Okay, because of this power equation, it will drop. Okay, not a problem. So what is the story now? It says, how would the brightness, okay, right, only increase, decrease, remain the same? So you and I already agree that this will effectively decrease because we lost the current. The brightness will have something to do with the current. All right, so it will decrease. And then they're telling us, explain your answer with reference to the relevant power formula. Well, this is pretty easy. So we will just use the power is equal to I squared multiplied by R. So we can see that if we drop that, and remember this drops quite significantly with the same resistance kept. So it would mean the power will effectively drop. Ne? Yebo. Yebo. I'm not even going to go into detail about that. So explain the answer with reference to the relevant formula. Okay. Maybe let's do this one properly. So we have 8.4. We know that it will decrease. Okay. So what is the explanation? The explanation is such that the total, resistance of the external circuit, external circuit will increase, effectively decreasing the total current of the circuit of the circuit. And so, okay, this means that the brightness of the bulb will drop, as seen with P is I squared multiplied by R. R is constant and the current is dropping, so the power will effectively drop, okay, because that is a constant that will drop and therefore the power drops. It's a direct proportion between the two. Alright, so you can have a lot of ways to explain this. You can say since power is directly proportional to the current squared, the current drops, therefore that drops as the resistance remains the same. Okay, Bafwetu, so that is that. So yeah, we are losing time, but I'm no longer interested in that, because if I am not explaining this thing, I'm much quicker than when I am trying to explain things as well. Now, question 9 says, a diagram below shows a simplified electric motor. Okay, what is it? It's a motor. Now, which type of a motor? You look here. Now, we have a split ring commutator, so that becomes a DC motor. Okay, those are the things that you need to quickly do. All right, so that is fine. And then, of course, north to south, the direction of the magnetic field is like that, with the current like that. So we use left hand, Fleming's left hand motor rule. So now you place your hand, index finger must point from north to south, the middle finger must point in the direction of the current, and therefore the thumb will point in the direction of force. So this means this force is down on this part, and then on this part, same story, the force is up, so meaning our little armature will rotate clockwise. So these are the things you want to quickly look at and be able to just deal with. So it says write down the energy conversion which takes place in an electric motor. We know that it is from electrical to mechanical. Okay, no problem. And then it says in which direction is the coil rotating? We've already established it's gonna go clockwise, right? Right, using Fleming's left hand motor rule. For motors, you use the left hand rule. Now it says name the component B. Now B is the carbon brush, okay? It's a carbon brush, okay? Now write down the function of component A. Okay, so this is now 9.1.4. So this is the split ring. Aibo. The split ring. What is the function of the split ring? It is to reverse the current. Is to reverse the what does it do? It is to reverse the current in the armature every 1/2 cycle. Okay, every 1/2 cycle that thing reverses the current, so that the current is moving just like this all the time. Okay, great stuff. So that is the main function of our split ring commutator. Now I told you the resistance R is now decreased. Okay, now remember this is a resistance, so it means we will have less energy dissipated. If we decrease resistance, what happens to the current? The current increases. You increase the current strength here, what happens to the force of rotation or the speed of rotation? It increases. All right, so now it says, what is the effect of this change in the speed of the motor? Choose from increases, decreases, or stay the same, and give a reason for the answer. The answer is it increases. All right, the reason is because the total current through the armature is going to increase. Okay, yani, maybe let's not even do this. Yani, ebafethu phelile ixesha manje, time pens down manje, it pens down esan. There's just one question to go, but you see, when you're not talking too much, bafethu, I promise you're gonna get this thing. You're gonna get this thing. So 9.1.5, is it? Yeah, so we said increases. Why does it increase? Because the current increases with a decrease of the resistance. So this is basically Ohm's law, ne? Easy stuff. So you get your 2 marks and you smile. Now let's get this 9.2 quickly. I'm tired. 9.2 says, a municipality experiences a temporary power shortage, which is not temporary in South Africa. It's permanent now. It's rubbish. It's ridiculous, man. Somebody needs to be donored. And I will find a way of donoring someone. During this period, the root means square voltage. Remember, the root means square voltage, RMS voltage, reduced from 220 volts to 200 volts. Okay, now the question says define the term RMS voltage. I mean, guys, these are easy marks. These are the things you just don't leave behind. Okay, so let's do 9.2.1. So the RMS voltage. So how do you define RMS voltage, guys? So you know your stuff, right? Is that the RMS voltage, it is the voltage used to determine the average power, okay, delivered by an AC source. You can just say that. Or you can say it is an AC voltage that is equivalent to the DC voltage necessary to deliver the same power. Okay, so maybe let's try the technical one. It is an AC, okay, voltage, okay, that is equivalent, all right, to the DC voltage, okay, necessary to deliver the same power. Okay, not a problem. All right, there's plenty of ways you can say this, but I think this is a bit of a fair one. It's fair. It's fair. Okay, you won't lose marks if you say it. Now the last question here says calculate the maximum or peak voltage during the power shortage. That means we're going to use that. All right, so we have here 9.2.2. So we know that, of course, peak voltage, okay, maybe it's Vmax. Let's use the word Vmax is equal to the VRMS multiplied by the square root of 2. Is that so? Let me just double check. Let me just double check. Before I start producing lies, you know, it's easy to lie with confidence. And people believe you, but only to ban for it. So, hey. Leskalafisa, ka baka la hore le ntse le mamela nna ha ke le thetsa mona. I lie, bafethu, I lie. So you must make sure you double check this thing. So maybe let's do this. Let's just write it properly before we start doing gymnastics on it. So we know that V RMS is going to be V max over the square root of 2. Ne? So therefore V max this time is going to be square root of 2 multiplied by V RMS, which is the square root of 2 times. Now they said it dropped from 220 to 200, so we're going to use the 200 during the thingy. Alright, so we have here square root of 2 times 200. So this is going to be 282,84 volts. So as you can see, the max is much bigger than the RMS voltage that we got. Okay guys, this was a standard 3-mark question. Formula, substitution, answer. Okay, we're almost done. Buffet 2. So just bear with me for a little bit. So formula, substitution, and answer. 3 marks in the bag. Okay, let's do the last one as quickly as we can. At least we didn't lose so much time. 10.1, it's photoelectric effect. Okay, they say now the photoelectric effect confirms the particle nature of light. Okay. Okay. Describe the term photoelectric effect in words. Now this time, you're not going to be using symbols here. You're going to have to use words. Yeah, when I think I described the Doppler effect. Yeah. You see this guy and this nonsense of talking too much. Yeah, when now it's coming to my mind that I did not answer the question on the Doppler effect. I think they asked a question as to what the Doppler effect, and then I started talking about electrons, which is whoop. No man. Forgive me for this one. This was the biggest crime ever. Now I started describing the photoelectric effect here instead. So this is not correct. Yeah, let's correct ourselves. I'm sorry guys for that. Sometimes happens. So the Doppler effect is described as the apparent change. Okay? I saw the Lentian puzzles. When it's continue. Is the apparent change in frequency. Okay? The apparent change in frequency of a wave. Alright? When there is a relative motion between between the source of the wave and the observer. It is the apparent change in frequency of the wave when there is relative motion between the source of the wave and the observer. So all bafowethu tshwarelo lintshwarele bana besu. I made a mistake there. So now this question helped me to remember that So I'm happy though that I'm making some of these common mistakes you guys make as well, so that you can guard against these things. Alright, so 10.1.1. So Doppler effect. You know what is that? It is the phenomenon whereby electrons are emitted from a metal surface when the light of sufficient light is shown on it. Okay, easy, no problem. So you make sure you say what you mean and mean what you say, okay? Now we're told here the work function of a metal surface is 5,6 times 10 to the minus 19 joules. Light of wavelength 450 nanometers is incident on the metal surface. Now the question says define the work function. I'm not going to go through that one. It is the minimum energy needed to emit electrons from a metal surface. Easy. Now we are here. It says now state the property of light that determines whether electrons are ejected or not, whether kinetic energy or not. But now what is this property of the light, not of the metal through which, on which the light is put, okay? So what in the light? It is its frequency, né? The frequency, because if this frequency is above the threshold frequency of the metal, then the electrons will come out. What about kinetic energy of the ejected electrons? Its frequency again. Because that is the one thing that is variable. Remember, energy is Planck's constant multiplied by frequency. This is constant, so this is the one thing that determines the properties of that light, is the frequency. So technically they're just trying to give you easy marks there, but by trying to confuse you as well and dent your confidence. Alright, determined by means of an appropriate calculation whether electrons will be ejected from this metal surface, okay? Now that means we need to find the energy of the light, of the photon. So we have the wavelength, which we can use to calculate the frequency, but we don't really need to calculate the frequency anyway. So what is this? This is now 10.1.4. So I'm jumping around Buffet to try and save time. 10.1.4. So we know first of all the energy of a photon is going to be equal to Planck's constant multiplied by the speed of light in a vacuum divided by the wavelength, because that's what they gave us. We don't have the frequency. Then Planck's constant is my information sheet before I start lying. So Planck's constant here is 6,63 times 10 to the minus 34 multiplied by, what is the speed of light in a vacuum? 3,0 times 10 to the exponent. Is it 8 or 6? It's 8. Okay. All of that divided by the wavelength. So this is 450 nanometers is times 10 to the minus 9. Okay. Nano means 10 to the minus 9. Ne? Yeah. So let's see if this energy is above the work function of that. So this is now 6,63 times 10 to the minus 34. You know what, guys? I'm committing a crime here. Times 3,0 exp 8. You know what? I'm committing a crime, guys. I'm working today. It's actually 4 a.m. now. I am working. I'm doing a lot of things today. And now I'm busy doing nonsense here. Okay, it's not nonsense, guys. You know what? You are more important to me than any of what I'm gonna be doing tomorrow. Because today it's already today. What I'm gonna be doing today, folks, is is second nature. Okay, second nature. I don't have to practice or think about it, so it's fine. I can go as tired as I will be. So let's just hope it works out. So now look at this, guys. This is 4,42 times 10 to the exponent minus 19 joules. What was the work function of this light? Of this metal is 5. So the energy of the photon. So we can say, therefore, no electrons will be emitted since the energy of the photon is less than the work function of the matter. Done. Remember, this is again formula, correct substitution, answer, and your conclusion. You get your 5 marks. Was it 5 marks or was it 4 marks? Yeah, that is it. Alright guys, let's do the last question now. It says now 3 electron energy levels in an atom are represented in the diagram. I would say to you guys, please note this one. I haven't really seen this one examined, so make sure you know it. It's gonna come in your finals. Now there's an increasing, so this is a lower energy level, a higher energy level, the highest energy level, okay, at least in this picture. Now we're told here the wavelength of the spectral lines produced. What is it? Wavelength. The spectral lines produced by the electron transitions between these 3 energy levels during emission is 486 nanometers, 656 nanometers, and 1880 nanometers. So the question is, which one is bigger? Because now we always think of the bigger one. So the one that is bigger is basically this one, because remember nanometers is going to be, say, 486 times 10 to the minus 9. Alright, so this is less negative than this one. So this one is the smallest wavelength, this is intermediate, this is the bigger wavelength of this one. So that is what is important. So the bigger wavelength basically is going to tell us about the energy levels, right? So remember, when we emit, it's when we're transitioning from higher energy to lower energy levels. So think of it like so. So what are they saying here? Copy the diagram above and draw arrows to show electron transitions between the energy levels that would give rise to these wavelengths. Label each arrow the wavelength of the emitted photon. Of course, we know that this becomes the greatest, all right, and then this becomes the intermediate one. You can see it's much bigger, but that one becomes the smaller one. I mean, doesn't matter even if you start with this one there or in between. At the end of the day, we know that the bigger one is that one, so we can write it here and say this is going to be the 4. Let's sort something here. So this is gonna be 486 nanometers, and then this one is going to be 656 nanometers, and then this one is gonna be 1880 nanometers. Okay, so the order in which you write these transitions is not really important, but what is important is them, because I mean this is the smallest difference in energy. That means a very, very, very silly wavelength over there, and then here this is a slightly bigger difference, so that means definitely a much shorter wavelength, or should we say a much what is this, a much higher frequency, and this is the highest frequency. So always know these things, which one is bigger, which one is smaller, and things like that. You know, shorter wavelengths mean higher frequencies, okay, and then longer wavelengths mean lesser frequencies, okay. So that is the story. That is the story. That is the story. That is the story. All right, guys. So this ends the story of this question paper. So at least I tried to not take forever doing it. And you know what? That is key. That is key. So yeah, Bafeto, that is the story. That is the story. So remember, this is based on frequency. So meaning the shorter wavelength In fact, I lied when I said this is longer, this is bigger. So technically, all I was trying to refer to is the frequencies, but technically is the shorter wavelength gives us the longer, the higher frequency. Okay, and then the longer the wavelength, it is the shorter the frequency, and frequency has relation to energy, because this is all energy. This is all energy, which is equal to Planck's constant and frequency. So think of it that way. So you're just basically converting wavelength to frequency, and you know they're inversely proportional. So the higher wavelengths make sure that we have less energy because of less frequency, and of course the shortest wavelength gives us the highest frequency, and that means the highest energy. So that is basically the story right here. All right, guys, I hope you've enjoyed the revision session. At least I took roughly 30 minutes longer than I was supposed to. So in essence, of where to, you can finish writing a physics paper in time. Probably you may not have enough time to review certain things, so you better make sure you plan very well. And in between, if you feel tired of a certain section, you can just go back and look in the one you jumped and see if you don't have an answer for it, because that is another way of trying to give yourself a very active break between, your answering of your questions. Otherwise, if you spot any issues, guys, please let me know. And then I would also advise you to have a look at the May-June physical science paper. I've done it, and multiple others have done it. MV tutors have done it. Lungis Nkosi has done it. A lot of people have done that paper. So you may want to go and have a look there and try to learn as much as possible. Just focus on the technique though. And you will see that the technique is very simple. You need to know your theory as well as you know your name, okay? Or your friend's name. And then you do the same thing of going, look at the approaches that are displayed by multiple presenters on these topics. The way one reasons through answering a particular question. Get into the habit of doing that. You will see that you will be a lot better and a lot more accurate in answering questions. Even the tricky ones become a little bit less tricky when you have that kind of a method, that kind of an approach, but it has to be solid. Of course, at this point in time, it may be a little difficult to learn that if you don't already have it. So whatever you already have, just maximize on it, okay? But if you are a student who's probably struggling to figure out any of these things and cannot really attach any sense to these things, I would advise you to attempt it. You still have time, because this is something you don't need a whole month or even a whole week to learn. You can learn it in a matter of a day, okay? Because you already have been studying throughout the year. There's things that you already know, but probably your acquisition technique, or should you say your recalling technique, is poor in that you are relying on just memorizing things. But you see, physical science is a logical subject. It has a lot of mathematics attached to it. So you would rather rely on placing logic as your tool to retrieve most of what you already know and perhaps can remember. And that way, you will sail through the exams. Of course, guys, I think I've done enough physics papers as well. The past papers, which are a little bit more challenging than these latest papers so far. So I would advise you to just look through in the channel. I tried to put them into a physical science playlist. Of course, they don't really look that attractive. I'm not really that person who cares for the looks that much. I care more for, the quality of the content that is presented, because that is what changes lives. And you'll be surprised how things that don't look so attractive are so useful and meaningful, but how things that are fleshy and colorful are really not so much of a use to a very desperate situation like this one. But I'm not discouraging making things colorful and more appealing, because at the end of the day, It's like when you want to buy a car. You wouldn't really buy a powerful, ugly car, right? But you would also want that car to be something that can be looked at. So please, guys, balance the equations. Remember, throughout life, you keep on trying to balance equations. There's no formulas, unfortunately, that are going to save you all the time, but there's techniques, there's experience of those who went ahead of you. When they share it with you, please make it a point that you add it to what you have. Don't make it replace what you have, because it may not be as successful as you think it will be. But add it so that it's an option. When whatever you know fails you, you grab hold of what you attached, and maybe it might just be your solution. But the take-home message from me, guys, is whatever you have learned, put it together. Don't discard what you have learned from someone else, but add what you're going to learn either from this video or any other video that you are going to be watching. At the same time, I would also tell you though that if you are to watch any videos, the best time to do it is maybe say tomorrow, as in today, sorry. You want to study this today, okay? Look at these videos today. Get the idea now. Get your mind into that mode. See how other people think through things so that your mind adopts that. Your mind has a tendency to always attach itself to what you expose it to. So that when, say, on Thursday, which is tomorrow, when you now start doing because you have to do, if you don't do yourself, you just watch, you're never going to succeed with these kinds of subjects. Maths and physics will always kick you out, because if you don't get yourself a moment where you actually do by yourself, unaided, then you're never going to be able to see whether you are strong enough, whether you are capable to doing it. And in fact, you'll get stuck and you will always think of someone who has the answers, but that someone is not there anymore. Then you'll just have yourself a very nightmarish kind of a situation that I don't wish upon anybody who's going to be writing these exams. So please, guys, if you want to watch videos, do them today, okay? Do them today, and do as many as you want, okay? But late today, try to do a bit of reading. Refresh some concepts, read definitions, look at, some sections that you have not really mastered. Read those sections fully, try to make a few notes there, and do some basic practices there. If there's calculations involved, do the very basic calculations that your textbooks or whatever material you have presents. Don't go for the exam type questions as yet. But once you finish those and you feel like you've got the concepts, go tackle the exam questions now on that section. Don't do the entire paper. Just go to question papers that have those particular questions in that segment, and then work through those questions. You will see how easy it's going to be. Then once you're done, okay, you can maybe take a video or two just to, kind of refresh, so that you are preparing your mind to action for the next day. Then you can watch a video or two that you think you like, that motivates you, but still is doing science and not just anything else. So that when you wake up tomorrow morning, which is Thursday, just go shower, eat your breakfast, you make up your bed, you do whatever you have to do in the morning quickly. Then you take a past exam question paper that you did not do any other time before, and I would recommend the older ones, not the new ones, because you've already worked through them now already, and multiple other people have done it for you. So just make sure you take an older paper and you try to do it as if you are doing that exam. And while you do it, keep your time. Try to go through the same exercises I'm telling you, how you reason, how you do a bit of brainstorming before you answer those questions. Don't worry about time that much, but worry about how close you will be at the end when you finish, how close you will be, even though you may be slightly ahead, slightly over the time that you're supposed to take. But the idea is you don't want to be far off that time, while you also presented quality of your knowledge right there. And then once you've done that, of course, you will see that you will have missed other questions, but most of the time it will be mistakes rather than no knowledge at all. It will be mistakes, sometimes maybe an idea that was not quite clear, and then of course you iron those out and repeat that paper. Don't mark yourself and think you've gotten it. No, the mind has a tendency to lie to you and say when you've seen someone do it, or you've seen the memo, now you know. No, you don't. You just don't. Look at that paper again later that day, but don't look at immediately after you've just marked it. Just let your brain forget about it for a while so that you can test yourself on it again, because those concepts that you probably missed are very important for your next exam. All right. And then of course you take another paper, probably one that we've done like this one. You can take this Limpopo paper, work through it, and you watch this video again, and you check the memo as well and see if is there any correlation that you can find. Are there any extras that probably are maybe explaining things better than the memo, or is the memo explaining things better than this one, so that you can also see maybe my confusions here are clarified in the memo. Maybe those were the confusions you would actually have. Now you will have a more clear vision of what you're supposed to do. So anyway, guys, I know I talk too much. Once I start talking, I never stop. So I would say, guys, I wish you good luck with your exams. I don't know. I don't like to interfere a lot with your quality time with your books now. This is where you need to really spend quality time with your books, but you can use these videos as your aids. You know what, when you feel tired of doing the reading and the practicing by yourself, but you don't want to waste time sitting there not doing anything, you can then watch a video to do that. Because trust me, when you're watching that video, your body gets to relax. You see, when you're moving your hands and you're writing and doing things and thinking at the same time, you know what happens? Your body gets tired because it's expending a lot of energy. But when you sit at relaxed and watching, you see your brain is always working even when you sleep. When you're dreaming, your brain is working. You're reasoning even inside the dream. So reasoning doesn't really expend a lot of energy. But the movements that you do when you write and do things is what actually makes you feel tired over time. So if you're sitting there and you're watching, you will feel relaxed but still engaging, okay? Then eventually when you feel like, okay, now you can't concentrate on the video, you can't really do anything, then this is when you stop. You go eat, you go drink, you go walk your dog out, or you do whatever you want to do, which is nothing related to this. And then of course, guys, sleep well the night before. Make sure you don't find yourself studying beyond 12 midnight. You can push it up to 12 depending on how much work you still need to do. But 12 midnight, go to sleep, and sleep 5 hours at least, but I recommend 6. So sleep from 12 to 6 a.m. and then wake up at 6:30 or so, get into your shower at 7 a.m., have your breakfast, or maybe 7:30. Then you can just do whatever you need to do before you go and write, but do whatever is necessary. Otherwise, guys, good luck from me, and I will try to do a chemistry paper as well from one of your trial papers this year to try and prepare you. Otherwise, watch as many of the resources there are on my channel as well as the other channels, and ones that I can recommend besides my own, which is not really that much informative anyway, but you can find something useful in my channel. But the others are quite packed, which is, you know, people like Mlungisi Nkosi, the MV tutors, NTE, there's many, the virtual tutor, you know, I mean, there's a lot of good guys there. So there's a guy there, Brilliant Minds Tutor. I like the way he does things, you know, I really do. So the guy's young, but you can see he's passionate, and his way of explaining things, I think, is remarkable from a young chap like that. So you want to look at those videos. I mean, this is just to mention a few quickly for you to have a look if you don't know them already. But there's plenty of people you can look at. Is it Kevin Math and Science? So the guy is a giant as well in teaching maths and physics. So you will learn a lot there. Otherwise, guys, hey, I'm talking too much as always, and I don't want to. So goodbye, guys, and good luck. So if you are lucky, I may drop a bonus video maybe early morning tomorrow. You will have it by 8 o'clock up and running. Maybe I might give you an extra on MCQs, maybe the more difficult type of MCQs. Maybe I can pick, say, 10 of them and then maybe do them as a bonus video just to make sure the MCQs don't make you shake when you are doing that exam. Otherwise, good luck and goodbye.